All right. Welcome everybody to our FDL 2022 live showcase. It's phenomenal to be able to share this work with you. In fact, I can't quite believe that we're here. It's been an amazing run, and we have a fantastic portfolio of research. In fact, we've never had so much research to present to you, and so because of that, we made this little graphic. In fact, well, I can say we asked an AI called Midjourney to make a graphic to celebrate this live showcase, and just a reminder of what AI can do, like this fantastic moment where we can ask an AI to imagine an astronaut having popcorn and somehow it imagines it's in zero gravity, and really this cool moment. But the stuff you'll see today is going to be even better than this. We're at this really amazing moment where AI can start to really tackle some of the greatest challenges of our time. And so welcome. It's really great to have everybody here. I'm going to pass it over to my colleague, Bill, and he's going to do an introduction to set the scene. And then we're going to dive into the research.
Yeah, thank you, James. Well, and welcome everybody from the SETI Institute here in Mountain View, California, where for the first time in, I guess, 2 or 3 years, James, we actually had the FDL teams back together in person for the first 3 weeks of the program.
Yeah, 3 dimensions.
Yeah, 3 dimensions. So for those of you who are familiar with the FDL program and have followed it for the past years, where this was our 7th year of the FDL program, which is, the applied AI and machine learning tools for space and earth science. And 2 exciting things happened this year. One being the fact that we were able to get the teams physically together for the program for the first time in 2 years. And second, that we welcomed the U.S. Department of Energy as another government partner in our program, joining NASA in what has been a phenomenal 6-year run up till now. And so we doubled the size of the program. We had nearly 100 people here at the Institute over the first 3 weeks of the program this summer, and the energy was just fantastic. And we're so excited about the results that the teams are going to share with you today. And James, it's too bad that Simon Cowell couldn't be here today. I know you think that Britain's got talent. I may think that America's got talent, but FDL has talent. And the FDL talent came from 19 different countries from all over the world, to the researchers that you'll be meeting today and hearing from today. So just amazing, very exciting, some really incredible results, and an incredible effort that these researchers and their mentors put in over a very intense 8-week sprint. The work that they pulled together in that time frame is just mind-boggling. I know, James, I couldn't even fathom being part of that effort myself, but delighted to have all of you here today. We have wonderful guests with us as well today, including from NASA, Department of Energy, our major compute partner, Google Cloud, and NVIDIA, another key partner for us, and others. So it's going to be very exciting. I think pretty fast moving, James, if I'm not mistaken, and looking forward to kicking this off.
Yeah, so this little intro, this welcome is really just a little bit like being at the red carpet at the Oscars. Of course, we're here
not as nicely dressed.
Well, you're pretty well nicely dressed. I could have done a bit better, but it's the FDL t-shirt. You see, I'm on brand at least. But this is about the research, of course. But we invited our partners to come and talk a little bit about it. But before we jump in, I just wanted, if you're new to FDL, just share a few slides just so you know what we're about. As Bill mentioned, we have this sort of huge plethora of challenges provided to us by our colleagues at NASA, but also for the first time this year from the DOE and the Office of AI. And we're covering earth science, astrobiology, energy futures, heliophysics, lunar exploration, climate adaptation, and disaster response. So you'll see all of that in the next 2 hours or 3 hours or so. And really it is a real proper kind of like goosebump stuff. So there's a lot to be excited about. But you may not be familiar with FDL, and so we thought, well, we have these amazing tools now. Why don't we ask DALL-E, which is an AI developed by OpenAI, to imagine what FDL is? And it sort of came up with this, which I thought was pretty cool. It's kind of like looking at the horizon and sort of looks quite techy, and then this one here again, sort of looking out towards the frontier, I guess. And then this third one made me laugh because it basically looked like Zoom, although in a very nice environment. I have to say, this is probably the nicest, some somehow chic Parisian apartment. But
these are all AI produced graphics, right, James?
These are all produced by DALL-E, yeah. And it's, basically imagine what Frontier Development Lab is, and it comes up with this. But in reality, this is what it's like. And this is, we just wanted to bring it to life a little bit for you. We are all about culture. We're about creating a group of people who just are able to do fantastic things by coming together. And this year, for the first time, of course, we were in person, which made it really even more special. And of course, that means all of those interpersonal connections get made, and we get to, hang out with our partners. You can see the team here going to Planet, and then some fantastic talks at at Google Cloud, and then Vint Cerf, who you may know invented the internet, which I guess we're all benefiting from at this moment. Thanks, Vint. He came and chatted to us, and then Steve Jurvetson, a fantastic friend of FDL. And so just creating this sort of culture of possibility, and there's nothing better than getting people together in the room to imagine and think boldly and then do amazing things together. So just wanted to sort of set the scene a bit, and just a reminder that you're going to be looking at almost like climbing Mount Everest. There's this kind of huge infrastructure required to do the work that you're about to see, but the researchers themselves only have 8 weeks to build the algorithm, the machine learning bit in the middle. We do this in the summer because that's the best time to get teams together, interdisciplinary folks who are both machine learning specialists and subject domain specialists. We bring them together, and then of course that's where the magic happens.
James, an interesting sidebar on that timeline is the fact that this 8 weeks, one of the things that enables the 8 weeks is all the work that goes on at the front end to select the research challenges, to understand the data sources, databases that are going to inform that research. So these are highly curated challenges, and our partners at NASA, Department of Energy, and our commercial partners as well put tremendous effort into getting essentially an AI-ready challenge put in front of the researchers. But the program, the endeavor is truly a year-round, culminating with this 8-week sprint.
Thanks, Bill. There's lots of data. This is way too complicated for a presentation, but I wanted to call out some numbers we're particularly proud of, and this is our DEI, diversity, equity, inclusion numbers. We are industry leading in diversity. This is something we really invest a lot of work in, we really care about. And this year we had 37% women. The industry average is about 22%, and we had 54% ethnic minorities. So we're really, really committed to this. We believe in diversity. We believe diversity allows more points of view, more possibilities, and I think you'll see the results of that in the work you're about to see. Thank you so much, of course, to NVIDIA, incredible resources. This is a DGX workstation you're looking at, which is really the state-of-the-art in GPU technology, and of course Google Cloud, this phenomenal global infrastructure that allows us to do the work we do. And so thanks again to our partners for that. So really changing gears now to the panel. Quick shout out. We always do open science. All our work is reproducible. This is something we care about. I'm going to jump this one in the interest of time, but really just to start inviting our panel to talk about what's coming up. And as you say, it's like we've got quite a very busy schedule, but I really wanted to sort of talk about the possibilities. And we've got Scott Penberthy from Google Cloud, we've got Lika Guhatha Kurta from NASA headquarters, Alison Landers from NVIDIA, Johnny Bradley from ATO, Bill Diamond, of course, and myself. And so really just sort of setting the scene for what's to come. And I'd love to sort of get sort of some first sort of thoughts, and in terms of kind of, well, we're in this sort of era of complex problems, of course, we care about here at FDL, and really just to sort of perhaps reflect on why AI is a potential solution for this. And Scott, because you're on the left-hand side here, I might pick on you first.
Yeah, I think this is, to me, they say Christmas in July. This is like Christmas in August for me, James, in terms of AI. I think what I love about this, I think Johnny was saying this earlier, is that we're actually seeing the future, right in front of our eyes. I mean, this is the next generation. I thought that was Johnny was saying that this morning. And, you know, what I'm just so fascinated about, you know, James, is that AI, when, you know, I used to study back when it didn't work, you know, many years ago. And, you know, the breakthroughs in 2012, in the same year that we also did CRISPR, we always thought, could it ever be a tool of science?
Yeah.
I remember when I first met you and Bill, I think in 2016, 17, you know, folks at NASA or SpaceX and others are like, no, like just no, because I mean, talk about a conservative culture, and they're very safe and they're very methodical. And James is like, no, we're going to figure out how to make AI a tool of science. And now we're seeing the impact of it, where, you know, you're just showing us with Dolly, and now, you know, we do AlphaFold, for example, at Google, and we're also seeing now these platforms where it's becoming almost second nature now, and the tools are becoming so powerful. These models that used to take, you know, all kinds of books you have to read and study just to be able to build one are 2 lines of Python now. And
That's true.
And it's just like, that's incredible. And,
It is.
you know, people coming out of school like, of course vision's solved, of course language is starting to work. And I'm just smiling, because when we started with you, it was just, you know, will this ever work? Will NASA ever pay attention?
Scott, that history, you know, you bring to light. I mean, this was back in 2015 when NASA first approached us and you know, came up with this idea with a lot of actually help and support from James and his team. But their first question was, you know, can AI be useful at all to base
is it
research
useful?
in NASA science? They didn't even know. It was a question that they wanted FDL to answer, and here we are 7 years later.
I know, Bill. And then, you know, like when we first got it, you know, the engineers came and showed, you know, Google leadership many years ago, a couple of years before that, and said, oh, guess what we found? What? Cats on YouTube. Really? That's the big breakthrough for AI. And we've come so far, James. I'm just delighted to be here to see, you know, how far the field's progressed. And just as Johnny was saying before, we're just kind of witnessing the future here. And, you know, Johnny, I don't know what you think. This is maybe your first year with DOE, but to me, this is just, it's just fantastic. And I love seeing all these possibilities that they're so far past me now. I just try to catch up. And, you know, just like, I think there's no experts in AI anymore, James. You got to be a student. And I think right now, I learn from you every time we see this, and I can't wait to learn more today.
Yeah, or use NLP, which is coming down the
event horizon for AI, Scott. That's what you're trying to catch up to, and it's an asymptote. We will never catch up.
Yeah.
Never. And it's just, anyways, I'm just lucky to be here with such an august crowd. And, you know, one of us doesn't belong, is probably me, but I think it's just amazing to see so many bright minds in one virtual room today.
Lika, have you got any thoughts? Grand challenges, AI?
Well, you know, I mean, don't give me any platform to stop you. But for my part, I want to say, you guys converted me from being an agnostic to a proselytizer, and, you know, kind of a career bureaucrat at NASA. Doesn't happen all that often, and you know that. I think what FDL has been doing is simply amazing. You know, we are learning by doing. It's not talk. Talk is cheap, but we are actually doing it over this 8-week period, taking difficult, thorny problems and shedding light where the real underlying physics hidden pattern might be, dispelling the notion of AI as magic. And that is happening very rapidly. And I'd say, you know, if you look at where we are at NASA today, where we were, say, in 2015, when you got started, we have Open Science Initiative. And Open Science is really going to be propelled by the tools and techniques of AI ML. I feel for the first time, I think we are beginning to utilize 21st century tools to do 21st century science. Instead of, you know, the tools and our academic training that is so dated. Finally, I love to kind of go back to what Stephen Hawking have said, because to me, it has resonated so deeply. I think that is the future. And I think AI/ML is an approach to tackle that. And so I'm going to simply read what he said. I think the 21st century will be the century of complexity. We have already discovered the basic laws that govern matter and understand all the normal situations. We don't know how the laws fit together and what happens under extreme conditions. There is no limit to the complexity we can build using the basic laws. And it is the basic laws with tools like AI, ML, that is going to create our future. That is our grand challenge. Zip.
That's great.
Thanks, Lika. Joni, you're at ATO. You're a strategist there. What do you think about the moment we're in and the role of AI?
I think the role that we are in is very important, and it's actually going to set the tone for the future. So it's very important to try to get this right now. I say it all the time to Director Isom. You have a million opportunities to get it wrong, but you've got one opportunity really to get it right. Not that you can't fix it later on down the line, but you want to get it as correct as you can. And I think with AI and ML, I think that using those types of strategies is going to be our best path forward to get us where we need to be. I look at, I eat and breathe and sleep energy, right? So I'm all about the problems that, that we have with climate solutions. It's critical because of, what we're going through in this climate crisis. I look at how we have our citizens with energy burdens, right? You have people, everyday people that have to decide, do I want to buy food or do I want to keep the lights on, right? That's a heavy choice to make, right? Between food and lights, because you really need both, right? So we have these issues, we have these people having these complicated discussions and complicated problems on a daily basis, and how do we resolve them? AI is a way to do it. We look at our grid infrastructure, it's in need of repair. We look at the climate change, it's evolving. I mean, literally right before our eyes. I now can see, I used to track, me and my sister, we have a garden out back, and I used to track every summer, well, where did the sun go? It used to be here, and then it was there. And, are we shifting? Are we moving? What's going on? The reason why now it's like the temperature is way hotter. I remember when I was young and used to love to play outside. As I am now today, I still like to go outside, but I wait until the latter part of the day, right? Because it's just excruciating. The temperature has risen, and it's just small things that even children can see. And today I just feel like I'm a student. Yesterday, I felt like an expert. Today I feel like a student, and I want to learn, and I cannot wait for everyone that is on this platform to see what's about to happen. The AI and the ML is real. It's true. People think I robot. I don't think I robot. I think solutions. I think things that will help this nation, that will help this world, collectively, not just here in the US, not just overseas. I think we're all one in this battle, and we have to take it very seriously. And like I said, we may have many chances to get this wrong, but we are in life and death situations where we have to get it right. And I think with programs like FDL, I think this is where we're looking at the future. Scott, just like you said, it's, we're literally getting ready to sit here and look at future solutions. And I mean, I get goosebumps talking about it. I get excited talking about it. And that's probably why Director Isom chose me to come in her place, because she knows I get really hyper about this.
She gets excited.
And I just feel like,
she does,
and I don't want to take up anyone's time, but I just want to say thank you for having me. I'm proud of everything that we're all about to see. I cannot wait to experience it. I have my cup of coffee. I'm comfortable and I'm ready to go. Just know I'm ready to go. So yeah, this is like Christmas and New Year's in August. All right. That's where I'm at with it. It's all of those, all in one. Yeah. Okay.
And we are definitely all in this together, especially
Allison,
the future.
Yeah, Allison, quick thoughts. I think we have because of time, we're gonna have some music play in when we're out of time. So if that happens, we know we need to keep moving.
My backing track, right?
Yeah.
No, I have to agree with absolutely everybody, but it's constantly evolving. So I love that whole mindset that we're being forced into, where you continually have to learn. Definitely no experts, because everybody is learning and everything's changing, weekly. sometimes monthly. You know, there's this real friction between state of the art and can we deploy state of the art, and we're going too fast for the people who are building the spacecraft and all that kind of stuff. But do you know what? I'm such a space geek, and everything space is just phenomenal for me. So FDL, of course, is just amazing, and all you guys, there's always such a huge buzz, and very, very excited today to see what everybody's done. But do you know what? There is nothing cooler than an autonomous robot trundling around the moon. You know, we've got our autonomous robots on Mars, but setting the way and getting us prepared for our return, you know, 24, 25, hopefully. There's nothing cooler than that. And we're going to learn, you know, about more work that's being done to help with that in just a few moments. But, you know, I always remember the quote from Interstellar, you know, that we were never meant to stay on Earth. You know, we were born here, but never meant to stay there. And we have to go back, you know, and if it's setting up, you know, the 7-Eleven on the moon and the gas station in orbit, which, you know, folks have already done, so that we can really start exploring and using all the tools like AI, then so be it. You know, let's do it. And we're making it happen with FDL. We're really bringing it to the front. That 8 weeks, I know, is painful for many, many people, if, you know, if not our fellows. But it's really crucial because it shows we can do it in 8 weeks, not let's take, you know, 4 or 5 years to think about this. Because right now, you know, people are running out of water. You know, just a few hours south of me, you know, there are hosepipe bans. Just a few hours further south in Europe, you know, the rivers are drying up. We can't wait around now. So it's really crucial that we just get on with it, and we're going to see some really cool stuff. But thanks again, so and you know, can't wait. Very excited.
Speaking of getting on with it, there's the music. Perfect segue, Alison. Bill, do you want to take the helm?
All right. Thank you very much. Thanks to all our panelists for that welcome session. That was perfect. And Alison, your segue into the first talk was right on the mark, because you talked about going back to the moon. And one of the FDL teams this year was focused on the moon as a dynamic environment. We think of it as this static rock that's been up in orbit around our planet for billions of years, and yet it is not just sitting there. It is a dynamic environment with tectonic activity, with impact activity. And if we're going back, we need to know about that dynamic environment and recent events. The Lunar Reconnaissance Orbiter has had a 13-year mission around the moon, and its Diviner instrument operating in the visible and UV has generated massive amounts of data that this year's team that you're about to hear from mined using AI and machine learning tools to look for changes in the data set that would demonstrate how the moon and the lunar surface and that environment has changed over time as we prepare to go back. So with that, let me introduce the researchers from today's Change Detection with the LRO Diviner mission team, and that is Ben Gaffinet and Sylvia Bucci and Zia Liang Kora. So I will turn it over to the team and let them take it away and bring us back to the moon.
We are at the beginning of an exciting decade for space exploration, in which we will first go back to the moon. But we still don't have answers to questions such as how frequently do new impacts occur, or are there changes on the moon that we are not aware of. The task of this challenge is to scan 13 years of LRO Diviner's dataset to detect changes on the whole lunar surface, such as new craters and landslides, to answer those questions. This would help to provide targets for future exploration, as well as identifying potential hazards for future robotic and human missions to the moon in advance of Artemis. The Luxembourg Space Agency would like to thank FDL for organizing this inspiring program, and the Lunar team for taking up this challenge.
one of the science goals of NASA's Artemis mission is gaining an improved understanding of the moon's and our solar system's history. We still don't have answers to questions such as how frequently do new impacts occur? Is there present-day tectonic activity on the moon? Therefore, detecting recent changes of the lunar surface is very useful to NASA. I'm excited to see if we can use machine learning to identify the faint and transient signatures of features such as fresh craters, landslides, and tectonic activity. This research will ideally provide targets for future exploration, as well as identify potential hazards for future robotic and human missions to the moon. NASA would like to thank our partners, the Luxembourg Space Agency, and of course the amazing research team for helping pave the way.
Welcome, everybody. Thank you for being here, and thank you very much for having us. We are the Lunar Exploration Team, and we are hunting for fresh craters on the moon. The moon is often referred to as the archive of our solar system. The craters on it are billions of years old, and they can form as a snapshot into the past of our solar system. Alongside the craters, other features like the canyons on Mars and the basins on Mercury are the key puzzle pieces to understand how the planets came to be as they are today. But just like with the bones in paleontology, there's a very important task, and that is dating back to when these surfaces have been created. On the left side, we have a very young surface, on the right, a very old one. One thing that is very apparent is that the craters are much bigger and more numerous in the right one. And actually, by counting the size and number of the craters, we can establish how old these surfaces are. But there's one very important factor that is needed, and that is knowing how many impacts there are within a given time frame, the impact rate, and that is where we come in. The LRO, the Lunar Reconnaissance Orbiter, has been gathering data for 13 years, and we are trying to find within this data set if any new craters have appeared. Teams before us, researchers, have done this with the optical data, but there's a big limitation, which is the illumination conditions that vary too much after 2 passes. Because of this, only 6% of the moon have been scanned with this method. But luckily, there's also thermal data available, the one that we are working with. And there's a very important and interesting physical phenomenon happening during an impact. When an impact occurs, the center is heating up, but it cools back down very quickly within a day or a few weeks. The chance that the satellite is actually capturing this is extremely low. But luckily, the seismic wave at impact is disturbing the regolith, the moon dust around the center itself. This is then settling down at a lower density, and during the night, it will cool down much faster than the regular area. These cold spots, the large blue areas that you see, last for hundreds of thousands of years. Yes, and by spotting those, we're going to know if we find new craters. Our solution is called NEFTIS. It's the New Event Perceiving High Trust, High Yield System. And this is how we do it.
So we are going to use data acquired from a satellite. For this reason, we need to deal with the problem of data sparsity. So we decide to aggregate the information over the years to create a unique image for the before and after for every point over the moon. So for the before image, for every point, we take the earliest measurement. For the after image instead, for every point, we take the latest measurement. So after this data preprocessing, we are ready to apply our machine learning solution. Our first solution is based on a binary classifier. So we train a neural network to recognize if the input image is or not a cool spot. After that, during evaluation, if we want to check if a point corresponded to a fresh cool spot, we produce the before and after image for the point. If the prediction for the before image is no cool spot and the prediction for the after image is cool spot, this means that probably in that point a recent impact occurred. The second solution that we implement is based on an anomaly detection technique. So we use as training data the background noise, that is the difference between the before and after image. So we train our neural network to learn the distribution of the background noise. During the evaluation, so at this time, if the input image is very different with respect to the background noise, so with respect to the distribution learned during training, then the network will output a very high anomaly score. And this is a sign that a recent change occurred in that point.
For the evaluation part, we will only have 5 non-impacts. So for each of the impact, we're going to select a large area around the location. Then we're going to run our methods to see if we can find it. And then eventually we can verify that with optical images. So here is one example showing how big the evaluation site is. Then we can further zoom in to see the detail. So as you can see here, the blue dot, the green dot in the middle is the non-impact detected by the traditional methods. And the blue ones are going to be the candidates by the anomaly detector. So to keep in mind that anomaly detector is not only able to find the cold spots, it's also able to find other type of anomalies, such as landslides or even moonquakes. And lastly, we have the yellow ones are going to be the candidates by the binary classifier. So as you can see, both our methods are going to be able to recover the null impact in the middle. So we can further check the details of each single candidate. We can check the before and after thermal images, and we can also clearly see the cold spot is present from the difference image. And the last step is to check the optical image. So here, the white dot in the highlight region is the impact, whereas the black regolith around it is the sign of the cold spot. So remember that we said we have 5 regions to evaluate, and amazingly, we are able to find all 5 recent impacts with both our methods. So in summary, our tool is able to automatically highlight all the potential new impacts for any area on the moon. And we can also auto-generate all the relative informations, such as thermal images or optical images. It's also worth mentioning that the whole process is really fast. It's only taking less than a minute to evaluate the whole region, whereas the traditional methods could take days or even weeks. So in conclusion, detecting the new cold spots on the lunar surface is going to allow us to have a better understanding of the impact rate on the moon. And a similar methodology could also be applied to other celestial bodies, such as Mars. So in the end, it will allow us to have a better understanding of the history of our solar system. Thank you so much for listening.
Amazing team. It's a bit unfair because we're going to have the response panel come after the next team, but means the only person who's clapping is me. But I just wanted to say that was phenomenal and really super proud of all your hard work and congratulations. But in the interest of time, we're going to move right on. We didn't explain at the beginning that we're clustering our presentations in teams of 2 and 1 triplet. And so these are the teams that have been helping each other for the last 8 weeks. And so we're going to go straight into the next team, which is our self-supervised SAR challenge. And we're going to get a short introduction from our stakeholder, Aaron Pina, who's the Associate Program Scientist at NASA, and he's going to introduce the challenge.
In NASA's Earth Science Division, we study nearly everything in the Earth system, from the top of the atmosphere to deep underground, including oceans. NASA's Earth data systems, which hold data from Earth-facing satellites, have over 40 petabytes of data, or equivalent to about 13.2 billion songs, or about 100,000 years of uninterrupted songs on Spotify. So about machine learning and Earth science, in NASA's Earth Science Division, our missions are about understanding our dynamic living planet. We use machine learning to help make sense of data from Earth observations and models. Some uses are for explainability or hypothesis generation, so think feature detection, uncertainty quantification, think modeling and analysis, and verification and validation. So consider the number of changes the Earth undergoes, from deforestation in the Amazon rainforest to a glacier melting in the Arctic, or to landslides in Puerto Rico. For the summer of 2022, I've been thrilled to work with a team on self-supervised learning on synthetic aperture radar data. I want to thank the entire team, their lead faculty member, Raul Ramos Poyan, our partners from the USGS, JPL, and Alaska Satellite Facility, and lastly, to all the FDL partners who helped make this summer a success.
Good day, everyone. I'm Ragini. Ivanis and me, we are super excited to share our team's 8-week journey here at FDL, where we have investigated how we can use satellite imagery to detect change on our planet using AI. I would like to introduce the Earth Science team. We like to call ourselves as the CSAR. We are made of 4 researchers, Ivanis, Vanessa, Viji, and me, and we have an amazing team of faculty who have guided us at every step. According to the United Nations, landslide in the past 20 years has affected 4.8 million people and caused almost 20,000 deaths. The rising temperature and climate change is only going to make this worse and trigger more and more landslides. In such a scenario, it becomes really crucial to provide timely and accurate data for emergency responses and decision makers. In the aftermath of a disaster such as landslide, commonly optical imagery is used to map the landslide extent, which guides and informs the emergency interventions. However, optical imagery has its own limitation, as it cannot sense at night and cannot look through clouds. As we observe on the screen here, our beautiful planet is always covered with clouds. We require a monitoring system that is independent of daylight, cloud cover, and weather conditions. This can be achieved with SAR. SAR is synthetic aperture radar, an active imaging sensor. SAR has the superpower that it can send signals to the Earth and record back the reflected signals. With this superpower, SAR can see through clouds and work at any time of the day. However, the SAR images obtained are complex to understand. While optical images can be simply interpreted as photograph, SAR requires a different way of thinking in terms of wave signal to interpret its different products, such as intensity, phase, and coherence. Though SAR is complex, it is rich in information. Can we use AI to extract this rich information from SAR data? Yes. The first step towards this is to lower the barrier for non-domain and machine learning experts by creating ML-ready, analysis-ready data cubes. Creating these data cubes was not trivial, as it requires expert-level knowledge for pre-processing SAR data, sometimes even up to 19 pre-processing steps to arrive at the SAR bands that is stored in this data cube. The other key component of this data cube is the label, which requires high human effort to manually look through the landslides and annotate them. With our custom data pipeline, we were able to create 4 analysis-ready data cubes for different landslide events.
The question now is, can we use AI to automatically detect landslides from SAR data? We start our analysis in Puerto Rico, where Hurricane Maria caused a lot of landslides. The dataset we have includes point labels that are the top of the landslides. The landslides there are small and also in dense vegetation. This makes the problem quite hard. According to experts, it might be an impossible task. And it has been very hard indeed. Several of the approaches we tried didn't produce good results. Eventually, we managed to have a model that combines SAR data with elevation data and does produce landslide density maps of good accuracy. So now we can imagine that instead of having experts go to the field and measure the landslides to produce landslide density maps like this months after the disaster happens, we can instead use an AI model that gets the data from the satellite and produces quickly landslide density maps. So we have the satellite looking from the sky, not being affected by clouds, and feeding data to the algorithms that produce density maps like this. Now we move on to Hokkaido, Japan. There we had some landslides induced by an earthquake which caused great devastation. For this dataset, we have the full contours of the landslides. So here we use a different model. We use a segmentation model trained to identify these contours. And in the validation set, data that have not been used by the model during training, we see predictions that very well match the labels. Actually, we can also identify that fusing data again, the SAR data with elevation data, can help us in early detection, can help us in what we want for rapid damage assessment. Now we move on to self-supervised learning. The problem in remote sensing for natural hazards is that many times we have a scarcity of labels. So the idea here is to use the input data and learn from that. The framework that we use is called masked autoencoders. And the idea is the following. We get the original data, we hide the big percentage of it, and we make the model learn to reconstruct the input. The hope is that this allows the model to learn a good representation of SAR data. We can then use this representation, we feed it to a very simple model that we see does very good predictions. In fact, these results are very promising, and they are very promising because they have great implications. They can allow us to handle the few labels, this label scarcity, but also it can allow us transferability. We can transfer to different areas, the same model for Hokkaido, for Puerto Rico, for Indonesia, and also to different tasks. So not only landslide detection, but also maybe flood detection. It can also allow us to use different bands of satellite. So we can use the C band and the L band that passes better through the vegetation. So after this work, we can be hopeful of a future that when a disaster strikes again, we will be more prepared. Together with Sentinel-1, we will also soon have NISAR. NISAR is a satellite that will be launched by NASA. It will operate on the L band, which passes through the vegetation, and for example, is better suited for Puerto Rico. And it will produce huge amounts of freely available data that then we can feed to our AI algorithms, like the ones that we saw today. And the results of those can inform interventions. And with that, thank you for listening.
Wonderful, thank you. That was, both of those were terrific presentations of the work that was done, and I think very good indications of the power of AI for change detection broadly, but also for predictive modeling. And I think one of the things that was demonstrated by both teams is the power as well for AI and machine learning tools to integrate data sets from different sources, combine them together, look at the connection between those to see how those data sets can inform by combining them a better understanding of given phenomena, particularly dynamic phenomena. So we're going to have a little discussion, a Why It Matters panel to talk about these two challenges. And we're joined by Megan Ansdell, who is at NASA headquarters in the Planetary Science Division, and actually one of the earliest FDL alumni. So it's wonderful to have Megan back with us. And we're also joined by Jason Stalker from the U.S. Geological Survey. So welcome to you both, and love to get your impressions on what you've just heard. And of course, Megan, you've got some inside knowledge of how this whole process works.
Yeah, I thought it was a short time when I was going through the program, but now I feel like just yesterday I was hearing about these challenges for the first time. So really impressed with everything that the team has got done. And I keep thinking about something that Scott mentioned in the opening panel about how we're finally doing AI for science. And it feels like even when I did the program back in 2018, we were just starting to do it. And it's really impressive to see things that I can really see have some significant scientific output. So that's the thing I was most excited about.
Absolutely. Jason?
Yeah, from a USGS perspective, change detection is really important to us. It's baked into our tagline, science for a changing world. I work on a program called the 3D elevation program that we do national scale mapping. And we've gotten to the point now where we have limited resources, and understanding where we can go to remap areas really depends on the areas that have changed. And so the work that the group has been doing using SAR will be a really key piece for us when we look for the areas that we know have changed to target higher resolution acquisitions, or even going out into the field to go out and map and measure. And for me, it's just amazing to think that these tools and technologies that were developed to do things like auto-completing sentences can now be applied to SAR imagery. Maybe someday we can get to the point where we're auto-completing disasters, and we can get in front of those and actually have some capabilities there to minimize the impacts, for example.
It's we've long said that time travel isn't possible, right? But Johnny put it in perspective in the earlier panel when you mentioned that this is the future. I mean, to a certain degree, these tools are giving us the possibility to time travel or to see the future in front of us. And this predictive capability that's associated with things like change detection, I think, is so powerful. And I guess, as we progress in FDL and applied AI and ML going forward, maybe what this will do is allow us to see further into the future and further into the future with more impactful insights. So I think that's absolutely true. And James, I don't know if you have some thoughts on that future path.
Well, actually, I was going to think, Jason, does this mean that you have less field trips to look forward to? I don't know how much you guys
there's always field trips to go on, James. I think we'll be fine.
Well, but now the thing is that we have, because of the work of the LRO team, Diviner team, like there's field trips to the moon, and Megan, I was sort of interested, to hear what you were thinking as you watched that and you saw of these new locations. I mean, could you imagine this sort of thing would be useful for your work?
Oh, totally. I was just thinking, like, it's preparing us for the ultimate field trip, which is to go back to the moon. And yeah, this change detection is so important. We know so little in some respects around how things change quickly in the solar system and on the moon. So better understanding of landslides, tectonic activity, impacts. It's going to help us plan for robotic and human missions to the moon that are coming right up. So this will be, I mean, it'll be amazing to see if we can use tools like this to help plan for future lunar missions.
Yeah, absolutely. I think the other thing that's interesting here is that what both teams have demonstrated is the power of the approach to be applied to other problems and other data sets. So I think over its history, FDL has not only been about specific problems, but also about techniques which are transferable to other problems and or other data sets or other types of phenomena. And both teams, I think, demonstrated that here tremendously, that we can take these same approaches and say, well, look what it did on this particular problem or question, and can we take that same approach and apply it over here? So I think that was terrific.
Yeah, definitely.
You go, Megan.
No, I was just going to say, it's one of my favorite things about AI and machine learning, just seeing the tools and how widely applicable they can be to completely different issues and challenges. It's one of my favorite things about it.
Yeah. I was just going to say, I wanted to congratulate the SAR team for saying, of all the things you could have looked at with self-supervised learning, we're going to do landslides, the hard one that the experts say no, it's not possible. And I just thought that image of the landslide through the clouds in Puerto Rico, what a great image that is. Yeah. Really awesome work, and congratulations on that.
Fantastic.
All right. Well, I think we could probably move on. And Jordan, we're probably ahead of time. That's why we haven't had the music. But I think I'm going to suggest we teleport to the sun And
the moon
thanks
to
to
the
our
sun.
panel. Yeah, and so we're now going to have a look at our two heliophysics teams, and we're going to get a short introduction from our good friend and colleague Lika from NASA headquarters, who's going to set the scene.
As solar cycle 25 is now getting underway, we are reminded that all of humankind's space missions, including the International Space Station and much of our nation's infrastructure in communication, surveillance, and navigation, including the critically important GPS GNSS system, are operating in this environment created and driven directly by the sun's emissions. Given all of the identified needs, a win-win situation is to develop various predictive capabilities that extract maximum value from scientific data through developing new approaches from combining data-driven methods, modeling, and algorithms capable of machine learning, deep learning, even in the face of limited, weak descriptions or identifications of physical elements and features. That is what the two heliophysics teams are tackling in FDL this year. The first one, the Sun as a fully resolved star. It takes days to build up solar emissions measurements across the Sun's full spherical 4π surface, and the result is an historical amalgam of the Sun. Solar structures change significantly within hours, and therefore a fully resolved 4π instance of the Sun requires measurement of solar irradiance across the full surface simultaneously. The resulting 4π data product will provide a valuable data product for solar and stellar studies and improve the forecast of space weather.
My name is Benoit, and my colleagues and I will provide an overview of our project titled 4π EUV Irradiance, the Sun as a Star. For this presentation, other than myself, you'll also be hearing from our amazing researchers Mira, Robert, and Margarita. The story I want to tell about the Sun is one of perspectives. The Sun drives all life on Earth, but it is also the hazard that our satellites and astronauts have to live with every day. For example, the extreme ultraviolet light, or EUV, that the Sun emits affects Earth's atmosphere in such a way that it degrades the orbit of the 40,000 or so satellites in low Earth orbit, with the risk of making them fall and burn in Earth's atmosphere. Therefore, we need to forecast the energy that the Sun emits in the form of EUV light to protect our assets. We call this the irradiance. What affects our technology might also affect life in general on other planets. By studying the Sun's interactions with Earth and other planets through irradiance, we may answer questions about the habitability of planets outside of the solar system. Additionally, since the Sun is the closest star to Earth, we have access to an up-close view that helps improve our general understanding of stars that are otherwise observed as distant points in the sky. But our story of perspectives doesn't stop at the Sun's impacts. It is also about how we view the Sun. The Earth orbits around the Sun. Its orbit sweeps a plane that we call the ecliptic. And current satellites are tied to the ecliptic, limiting our view of the Sun to its equator and not its poles. The Solar Dynamics Observatory, or SDO for short, is a satellite that takes pictures of the Sun from the Earth's perspective, and it is the only satellite that measures irradiance. For forecasting irradiance, this is problematic, as we do not know what's coming in the near future, only what is happening in the present. The single viewpoint limits our forecasting capabilities. But speaking of additional viewpoints, the stereo twin satellites were launched with orbits ahead and behind Earth's. But these satellites only take pictures of the Sun in EUV. They don't measure its irradiance. However, a previous FDL project has shown that the EUV irradiance can be predicted from EUV images. Which brings us to the main question of our challenge. how can we observe the sun and solar radiance from any perspective?
So, as Benoit has explained, we are currently locked onto the ecliptic plane. One solution to this would be to just add more satellites like SDO, but each of these satellites would cost about $1 billion each. And so the solution we propose is to add virtual instruments using machine learning, all for a fraction of the cost. These virtual instruments can be placed at any angle and at any time around the sun, and they can also measure irradiance, the amount of radiant energy coming from the sun. More specifically, our goals are to use machine learning to create virtual instruments that can observe the sun from all angles and estimate irradiance from any perspective. And we've done this with our machine learning pipeline called SPIES, which stands for the Spectral Irradiance of a 3D Sun. And we start with the existing perspectives we have from our original 3 vantage points. We will then feed these images to a type of neural network called a neural radiance field, or NERF, that will generate a 3D reconstruction of the sun. More precisely, we've created a NERF that translates the pixels of our images into a model of how much energy or light is distributed across the sun's atmosphere. We can represent this energy from the sun by encoding how much light is absorbed and emitted at a given location within the sun's atmosphere at a given time. And from this 3D reconstruction, we can then generate novel perspectives from beyond our limited viewpoints. We then feed these images from the novel perspectives into another neural network called EfficientNet that estimates the irradiance. And now I'll hand it over to Robert, who will reveal our final results.
So with this approach, we can create the first 3D reconstruction of the entire sun. With only 3 individual observations, we fully recover the geometry of solar features and create observations at arbitrary viewpoints. This means that our telescope is no longer tied to observing from Earth's perspective, but can be moved freely to any position in the solar system. While the original observations are all obtained from a single orbit, we can now even reconstruct the first complete image of the solar poles and view solar eruptions from all angles. With this, our method provides observations that would otherwise require multiple new satellite missions. These novel views can then be used by our virtual instrument that translates EUV images into solar irradiance. But how can we know that our reconstructions represent the physical reality? Our method creates unprecedented views, and there are no direct observations that can be used for comparison. Instead, we focus on the ability to forecast. For this, we build on the delay between the individual observations, where we can compare the predicted solar irradiance with the actual value that is measured when the sun rotates into view. As shown in this example, the predicted irradiance by our new virtual instrument is in agreement with the actual measurement that is obtained 12 days later. With this, we show that our method provides the next generation of space weather forecasts, where we can now determine the total energy at any viewpoint and can provide an early warning several days ahead. And going even further, we can determine the solar irradiance at other planets like Venus and Mars. Especially for future manned space missions, we can now determine solar impacts on Mars. For Earth, irradiance affects our space technology, but for other planets, it can be determining for the existence of life. With our approach, we can estimate irradiance for arbitrary planetary orbits, which gives us a unique way to study habitability for exoplanets that orbit sun-like stars. With that, I pass it on to Margarita.
So to summarize what we have achieved, up until now, the only images of the sun we have available are taken from the 3 satellites, which are in the orbit of the Earth. With our machine learning pipeline SPIES, we are now able to view the sun and spectral irradiance from everywhere in the solar system. And we are now able to have a virtual instrument that can fly out of the ecliptic. And repeating what Ben mentioned earlier, why does this matter? Changing the way we view and study our closest star will not only help protect our assets in space, but it will also help humanity know what to expect as it takes its first steps towards visiting other planets. Thus, it makes it possible for us to connect to other worlds and to the millions of stars out there. Thanks to our partners for the support, and thank you all very much.
Fantastic, thank you. Well, this is absolutely extraordinary work, and it shows not only the AI and machine learning capabilities for future prediction, which we've been talking about, but now what you've demonstrated is the ability of AI and ML tools to actually offer different perspectives, to see the unseen, to actually allow the visualization and understanding of phenomena from places that we can't directly observe. So just extraordinary. So sticking to that theme of prediction, here's another big question about future prediction. Can we predict earthquakes? Is it possible to have precursors for earthquake that give us days or even weeks of advance notice? Well, it's been long considered possible and likely that massive rocks under extraordinary stress emit electromagnetic radiation that might perturb or disturb the ionosphere in ways that could be measured. But the ionosphere is an extraordinarily noisy and active environment. So can we detect and pull the signal from the noise and actually see if electromagnetic precursors to seismic events on our planet can be eked out of the data? So with that, I'm going to turn us over to the seismology detection team. This is the team called Seismic Insights within Geomagnetic and Ionospheric Data. And our researchers today are Andy Smith, Asadullah Hill-Ghalib, and Luke Cullen. So with that, let me turn it over to the team and take it away.
Seismic insights within geomagnetic and ionospheric data. Now we know that electromagnetic precursors have been considered a promising means of earthquake prediction. However, there is an unsolved problem of how to find persistent earthquake-related precursor signatures in geomagnetic as well as ionospheric data. A major obstacle has been the difficulty in excluding the space weather effects that account for most variations in these data sets. So the team turned to ML to answer this question. I wish both teams good luck with their closing presentations.
Hello, everyone. Hello, everyone, and welcome to the Seismic Insights within Geomagnetic and Ionospheric Data Team Challenge. So, if you haven't grasped it from that catchy title, we're talking about earthquake forecasting. And earthquake forecasting could help prevent tens of thousands of deaths per year. And now, I realize we have a largely Silicon Valley-based audience, so I'll translate that to it also being able to reduce our costs in $34 billion annually. There has been mounting circumstantial evidence from recent case studies for precursors in unconventional data sources. Now we come back to those words that were in the title. We're looking at the geomagnetic field which surrounds the Earth and the variability of which we can measure from stations on the ground. We're also considering the ionosphere, which is a layer of charged particles that lies between 80 and 600 kilometers above the Earth's surface, the density of which we can probe with GPS signals. Okay, so to confront this challenge, we've assembled the mighty team of Andy Ghalib-Devra and myself, Luke, along with our advisory faculty with experience ranging from space weather through to machine learning. So what could possibly go wrong? Unfortunately, the small signals we expect to detect from earthquake signatures are swamped by the vastly larger signals emanating from the sun, which cause the beautiful aurora, but in our case, are a large source of noise. So imagine you have a needle, which is our little earthquake signatures, and amongst the haystack of other signatures coming in from mainly the sun. Just to add some interest, we also don't know what a needle looks like. So our first step was trying to identify the nature of the signal we're looking for. To do that and mitigate for other space noise, we looked at a whole range of earthquakes from around the world that you can see on the left here, and filtered them for large earthquakes, so magnitude above 7.5 events. And we looked first at a more accepted phenomenon, which is gravity waves after the event itself. And right enough, we found that consistently we can see a disturbance here on the right-hand side in the ionosphere in the hour to hour and a half after an earthquake. So, having validated this concept, we then moved to looking towards precursors. And what we discovered is that precursors are much more dependent on location and earthquake type. So here we have magnitude above 7 earthquakes from the Japanese region, and you can see that between 3 and 7 hours prior to the earthquake, there's a consistent drop in ionospheric density for these large events. So it's not as obvious as a signal for the aftershocks, but it does give us some hope that building a more complex model may be able to tease out these signatures for particular events. So we've identified what the needle might look like. So let's build the haystack. So we assemble our data sources that we've talked about previously, and through some unfortunately non-trivial feature engineering and time alignment to have the appropriate data for the earthquakes, we optimize to get to what we call our machine learning ready data. So, okay, we know what the needle looks like. We've got the haystack, and now we'll pass you over to Andy to tell you how we're going to look for it.
Thank you, Luke. This is a really tough problem. So we've actually attacked it in 2 different ways. The first is a direct method. So we're designing models here to predict if an earthquake has happened or if it will happen. The second method is indirect. Do earthquakes cause anomalies that will mean models of the ionosphere will give us terrible results? And can we use that discrepancy to then say an earthquake has happened or will happen? For the direct approach, we've tested an entire suite of models, from simple linear-based models all the way through to those based on deep learning. Ultimately, the performance was mixed, and the results for the best performing model are shown on the left. For context, I've included here the accuracy of a coin flip in this case. So for earthquakes greater than magnitude 6, we get slightly better accuracy than if you flip a coin in this setup. For slightly larger earthquakes, so those larger than 7, the performance goes up a little bit more. One of the things that we wanted to test though with this is whether this is a problem with the models and whether they can identify the patterns we need. So we designed a test with synthetic data where we put in earthquake signals that don't really exist. And then we tested our models on that. And the performance there was much, much better. So we're looking at performance now of about 96%. Ultimately, this leaves us with 2 options from this avenue of attack. Either the signals are too small in our data, or the data are not good enough to resolve them, or we need more data. We need better data and more of it. Okay, so can our indirect approach make some progress in this? Earthquakes are a regional disturbance, so we designed a regional ionospheric model to test this. The model uses the outer region here, so the outer grid here, outlined in red, to predict the properties of the ionosphere in the center box. Here we're showing it for an earthquake in northern Japan. On the right here, I'll animate how the model error changes over time. If the model is perfect, it will be a horizontal line on the 0 line. But realistically, we expect it to wiggle around this green zone here. So what we see is that's true before the earthquake, generally for this case. But then after the earthquake, about 10 minutes after it, the model performs catastrophically badly. And that's actually excellent. We can use this large error in the model to say that something strange has happened in the central zone. In this case, an earthquake has happened. These are the gravity waves that Luke mentioned earlier, messing with the ionosphere, meaning the model's predictions aren't as good. So can we use the same approach to predict earthquakes? Here we have a very similar model, again over northern Japan, and again we're using the outer regions to predict the middle. This time we're using a slightly different prediction of the ionosphere, and we're looking a bit further before the earthquake, so a day in advance. What we'll see here in the video is that generally the model starts off performing pretty well, wiggling about in the yellow zone. But then about 20 hours before this earthquake, the model has a preference for being below 0 and mostly within the orange zone. Something is not normal in this central region. And sure enough, in this case, there was an earthquake later on. This is our most promising approach so far, but we do need further work to validate it. We just have time for a quick summary of our whistle-stop tour. So firstly, we have confirmed the presence of consistent patterns before and after earthquakes and linked these to where they happen in the world and their type of earthquake. Secondly, we built a pipeline to generate global machine learning ready data. And this pipeline is open source and ready to ingest whatever data people can throw at the problem in the future. We've also tested an array of AI models to directly identify and forecast earthquakes. And these models perform excellently on synthetic data, but ultimately we need more or better data. And then finally, we have an indirect approach that in fact may work better in this case. Thank you very much for your time, and thank you to our sponsors and our faculty.
Amazing team, and I feel a bit. I don't envy the panel. We're going to go into the Y panel now for basically being shown the Mona Lisa with both of those two projects, and then having to respond to it. But I wanted to introduce our Y panel. I know we've got Lika here, who we've already met from NASA headquarters. Massey, who's distinguished technical director, applied AI at Google Cloud. Tom Berger, Space Weather Technology Research and Education Center. Of course, Bill as well. So yeah, just really quite amazing to see those two results back to back, and really would love to just get your first impressions and what you think. And looks like we've got Massey there. Do you want to take us or set us going, Massey?
Thank you. So, first of all, congratulations to the teams. This is actually amazing results. I love actually, Lika in the introductory video actually spoke about data products. I think actually this is a great input from these teams. They're not just kind of advancing the status quo of research here, and to what we said actually at the beginning of the discussion, they're applying AI to science in a way that has never been done before, but also creating data that can be used then by other researchers to kind of further actually kind of this research and get more insights. And I think actually that's actually that kind of network effect that is going to make this even more valuable. It's actually 10xing the work that they're doing. I also kind of, congratulations on applying AI in ways that is so innovative. I mean, I love NERF actually, for those who are not in the eye. It's something that kind of was published actually first time a couple of years ago. And those teams are already applying it to kind of solving scientific problems. So this actually is a great feature of FDL, of bringing together those people and advancing scientific research in ways that are kind of so important. I would say that, I think actually understanding the sun better and kind of solving some of those problems, it's really important. The sun is definitely kind of, our powerhouse. It powers life on Earth. And it's incredible. I mean, every time I talk to Lika and some of the solar scientists, how still actually kind of how lot actually we have to understand of the sun. And part of the problem is that it's a super complex system. And so I think it's the idea of applying AI to look inside the haystack is great. And kind of I love the way in which the teams have used data and computation to do that. So congratulations.
Thanks, Massey. So speaking of heliophysicists, do you want to, Lika and Tom, do you want to respond to what you just saw?
Sure, go ahead, Lika.
Well, I think in the introduction, I kind of tried to capture what these two groups have been attempting to do, and actually seeing the demonstration is pretty breathtaking for me. And yes, these are perhaps small steps, but think of the quantum leaps they will make in the near future. With the EUV, we have mission concepts where we want to send missions to the poles of the sun, really to get that magnetic field measurements. It's a critical measurement to really complete a more fuller understanding of the magnetic field, how it's created, destroyed, preserved, how it creates the very environment we live in, and to see the group kind of utilizing observations that we have taken for so long, trying to synthesize them and create this synthetic view of the sun. I think this is powerful stuff. This is actual physics that we support with our research and analysis tools. I think there's so much to come from this particular area of investigation, because EUV, extreme ultraviolet, affects us in so many ways, even as going far away from our own planet to Mars or other exoplanet environment someday that we might come upon. This will be sort of the benchmark type of measurements that we will need. And with the seismic insights, it is just that. It is telling us how difficult the problem is. And so this was really sort of a quick take on bringing everything we have to date that was available to the team over these 8-week periods. What we have to do now is really pull in more data, larger scientists, this will require much bigger effort to really pull those very faint sort of signals that exist. And it's not ionospheric disturbance, some of which is really propagated through the sun, how that impacts earthquake. But earthquake perhaps leaves some signature in the ionosphere too. So often we think sun as the driver. It is the most powerful driver, but there are disturbances also affecting this ionosphere, a very important region for space weather that is coming from below. Amazing stuff. Thank you.
Yeah, I'll echo that. Thank you to the team. Great job. I really enjoyed the presentation and watching it develop. I would add on to what Lika said in that the earthquake prediction may have been difficult, but what you really did was explore the parameter space and show. I really like the exploration of the complexity of models versus the phenomenon you're looking at, because that's very valuable to us researchers in solar flare physics as well, and solar flare prediction. That's exactly what we're up against. Solar flares are rare episodic phenomenon. They occur on these different scales. And having this sort of exploration of a similar phenomenon come out with a result that we can use, namely that the complex models don't necessarily do better. We should maybe be looking at smaller models, simpler models, was really helpful. And I'll just finally add that the ionospheric post-earthquake signal can be used to forecast tsunamis as well. So you've shown a really useful signal that can be used for not only predicting earthquakes, but predicting the effects of earthquakes after the event itself. So really great job.
Thanks, Tom. Yeah, I think the fact they've got a tsunami detector working is a really big achievement just in itself.
Yep.
Bill, I think you have the helm.
Okay, wonderful. Well, I think, an emerging theme here is FDL demonstrating AI and machine learning techniques for not only seeing into the future, but preparing for the future. But also, when you look at the difficulty of some of these challenges, what really pops out as well is how much further work needs to be done. So with every question we answer, we raise 10 more. We're going to jump ahead into further grand challenges. The US Department of Energy launched the Hydrogen Energy Earthshot in 2021, which was a response to President Biden's Climate Summit request to accelerate progress towards tackling the climate crisis. So the next team investigated whether or not we can use AI tools such as natural language processing to harvest and explore both historical and emerging research and determine candidate processes that might scale up to useful levels. So can AI help us discover new ideas and perhaps identify and rank the most promising ideas out there? To take us down this path and explore this, we have our researchers, Olabanjo Alasola, Rojan Yasai, Paul Surin, and Joseph Wiggins. So team, taking us away and into the Hydrogen Earthshot Challenge.
Famed adventure writer Jules Verne wrote, "I believe that water will one day be used as a fuel, that hydrogen and oxygen, which constitute it, used alone or simultaneously, will provide an inexhaustible source of heat and light of an intensity that coal cannot have." For a long time, many have thought that hydrogen, the most abundant element in the universe, could hold the key to a clean, sustainable, and equitable energy future. Nearly 150 years later, our planet faces a climate crisis, and we must take action to turn fantasy into reality. Department of Energy Secretary Jennifer M. Granholm announced the Hydrogen Energy Earthshot to accelerate breakthroughs of more abundant, affordable, and reliable clean energy solutions within the decade. We know that hydrogen can reduce greenhouse gas emissions, particularly in hard-to-decarbonize sectors such as industry, heavy-duty transport, and enable energy storage. The goal of the Hydrogen Shot is to decrease the cost of clean hydrogen production by 80% to $1 for 1 kilogram in 1 decade, or 111, to unlock new markets for hydrogen and enable decarbonization across sectors. Like the moonshot before it, we are setting aside our fears and choosing to tackle this challenge not because it is easy, but because it is hard. We hold on to the same spirit of adventure of those who came before us in this mission. Can artificial intelligence and machine learning help us uncover the most promising pathways to achieving the hydrogen shot goal. Our team is fearlessly exploring the depths of scientific knowledge and using new and advanced techniques to find connections between exciting new materials, methods, and systems to help us understand their potential impact on the cost of hydrogen production. I am so excited to introduce our team with the heart of adventure, the Hydrogen Discovery Engine.
Thank you so much. So I'm Joseph Wiggins, and this is the H2 Discovery Engine team. So what will, the first thing I want to start on is just looking back on some of the grand challenges of the past and the great things that we've been able to achieve, especially through the use of fuel sources like hydrogen. And this new generation has a new set of grand challenges, one of which is the energy Earth shots that was established by the Department of Energy. And one subcomponent of that is on hydrogen specifically. And there's this really ambitious goal to reach $1 for 1 kilogram of hydrogen in the next decade. And there's a tremendous potential in this idea to have a green, like a green resource for energy with what would be called like green hydrogen. But currently, this is not the reality of hydrogen. So currently only about 4% of hydrogen that is produced is considered green hydrogen, with the majority of it being considered blue hydrogen, which means that CO2 is created and stored, and then 46% being gray hydrogen, meaning that it's emitted into the atmosphere. And the reason for this is truly an economics problem. So we have, there's a lot of research being done, but it's still not feasible to go 100% with the green solution and be reaching our economic goals. And so what the Department of Energy is really faced with here is a multi-pronged iterative problem where they have to make funding choices that are going to help innovate in this space. Then that's going to influence novel innovations that they need to be able to observe. They then need to be able to assess the opportunities for cost reduction and then let that affect the funding choices in that next phase. And even over the last few weeks, you can see on the right, there's been so many innovations in hydrogen, and this is, I think, within 3 weeks. These are just some huge things about using capillary action to improve electrolysis design and to store hydrogen in an entirely different way, making it into a powdered form versus a gas. And so our team tackled this problem of trying to help the DOE make better decisions using natural language processing and graph neural networks. And we're excited to show off the tool, the H2 Golden Retriever. So the idea is that it can help dig through all this data that's coming out and kind of help spotlight things that'll be important for what we should fund in the future. So the one important thing about our design is that it heavily has the human in the loop. From the very beginning, we've been communicating with the Department of Energy. They've been a tremendous asset in helping us understand how what is the current state of hydrogen. And through that, we built these representations of their knowledge and expertise and what they thought was important, encoded that into ontologies, and then gathered up other things about economics and organizations, feeding all those into our natural language processing units and generating knowledge graphs. Those look a little something like this, where we take a paper and instead of it just being something you have to read, it kind of blows out into its connections with other materials and things that it mentions and metals that are important for the process it's talking about. And these are automatically extracted. One of our researchers spent the 8 weeks reading nonstop, and he probably got through about 500 pages. When we were finished with this over one night, Alushla and I ran this set over around 20,000 pages, and we woke up at it, processed it. And that opens a lot of doors. So now we have all this data that we're able to ingest. And we feed those knowledge graphs into graph neural networks to help us understand how thorough are these papers, how should they be ranked and presented in the UI and then given to the experts. And then finally, there's a concept called the causal decision diagram, in which we try to help visualize actions that they can take and then potential outcomes it would have on the cost, all in order to reach this 1-1-1 goal. So the tool is live. We're still iterating on it. There's 4 pieces I want to highlight in today's talk. So we have a semantic web that we're going to go over, an ontological view, a component cost breakdown, and then an investment modeler for this 1-1-1 goal. And I just want to mention that the items 3 and 4 were done with the help of psychologists from SFU in Canada, and they've been a tremendous asset. And so let's say that you wanted to know about catalyst cost optimization. If you typed it in the tool currently, this is what would pop up. And so in the middle, you see the concept, and then you see how it kind of shoots out and connects with all these other concepts that are important, like an electrolysis machine, so such as the membrane. And if you click on that, you can actually explode out the papers and see what is the what papers currently have those concepts in it. This also allows you to look at things that are not heavily researched at the moment. For instance, catalyst-coated membranes are much smaller in comparison to say like the standard membrane, and yet they're a very promising approach for optimizing this. So these sorts of visualizations help the experts kind of understand where the research is flowing and how it's changing. Secondarily, we were working on how to use the research knowledge to help both scrape, order, and sort the data. And so in kind of a phase one, we come up with a diagram like this, where we're understanding how pieces are connected and sort of the physical components are built. And then that evolves into like a landscape like this, where they can kind of zoom in on the physical system. And let's say you want to look at these catalyst-coated membranes inside the cells, and you kind of zoom in piece by piece, and you can find the papers connected to specific components. We also really interested with the costs. So we did a lot of work on, looking at where are the costs in the system. Not all pieces are costing as much to create these. And if we are, going to make this affordable, we have to really tackle those high costs. So we represent things like the actual cost in the current system by thickness. And you can blow those out and look at what subcomponents are truly holding up that progress towards that economic goal. And then finally, we model things about cost projections. So how much do you think things are going to change? What are the things that you can invest in, and what papers are currently like focused around that topic? And then finally, how might that affect kind of the cost future? So how is that getting us closer to that ideal goal? So the H2 Golden Retriever has all these components kind of brought together into our interface. And like I said, heavily we talked with the DOE. We brought this to them and did a series of workshops. And together we were able to come up with some really interesting ideas about how we could advance this and use AI in different ways, such as trying to reduce down information to critical components, combine different parts that are promising and look at research that's innovating in those spaces. And then also think about what concepts are staying in academia versus moving into, say, like into the industry. As we end this, I just want to thank my whole team, a bunch of individual components that, when arranged in just the right way and given a little bit of energy, produce wonderful insights and knowledge. Thank you so much.
Wonderful. Thanks so much, H2 Discovery. And if it wasn't obvious, any NLP project requires a vast amount of engineering, and I just wanted to congratulate you all for like the countless hours required to get to that level. And it's phenomenal to have these tools, and of course generalizable not just for H2 but a whole plethora of problems that we're facing. So with that, I'd love to also change gears and look at our other NLP team and introduce our Science Mission Directorate Knowledge Discovery team.
It seeks to answer a number of questions about the universe, including, are we alone in the universe, and how does life originate? How does the universe work? How and why is Earth's climate changing? The answers to these compelling questions are found in the wealth of data made openly available by NASA. Enabling discovery of these data and information is useful to both NASA and to the broader scientific community. We asked, could we leverage natural language processing techniques to provide scientists with an enhanced search and discovery experience that exposes useful connections to data? This project is unprecedented. Bringing together content from 5 unique scientific domains is a challenge. But success will help scientists to answer some of our biggest questions about the universe. Therefore, I'm excited to introduce the work of the SMD Knowledge Graph Discovery team.
Hello everyone, I am Megan Mark and I am here today with Fexen, Marcella, and Rolene, and shout out to our great mentors, Gregory and Anna Maria. We are the Science Mission Directorate Knowledge Graph Discovery team. Bucky Fuller saw knowledge as an expanding sphere, and the rate of this knowledge growth is called the doubling rate. This growth is a huge problem because the knowledge and the data is increasingly becoming more and more cross-domain or across different fields of science. And it can take scientists hours to find what they need, and it can be like finding a needle in a haystack. We can dramatically cut the time scientists spend looking for this data through the use of AI and knowledge graphs. So a knowledge graph is a tool for understanding how concepts are connected. For example, we have Apollo, and it is the node, and it is connected through an edge to John F. Kennedy. Well, John F. Kennedy is connected to the United States Agency for International Development, which is then connected to Surveyor. Surveyor provides satellite data to developing countries and works with Kenya. So Apollo is related to Kenya, and you wouldn't know that without the discovery power of a knowledge graph. We can use machine learning tools like natural language processing to tackle this challenge and to help accelerate new discoveries for NASA. For example, what if there was a cancer researcher who wanted to better understand how solar radiation affected astronauts for when we go back to the moon and Mars? Well, that cancer researcher might start with solar radiation, but as you can see here, there is a lot of data and they might not know where to even start. Wouldn't it be absolutely mind-blowing if this researcher could just go somewhere real fast, get the data they need, and answer those important questions? Our knowledge graph can help them do that. And we can build it by applying our pipeline to the text that describes all these data sets. To build the initial knowledge graph, we took all of these terms and information, and you can see that it is already getting really big. You can see there's 3 million terms in the Science Mission Directorate alone. So Marcel is going to tell you a little bit more about how this pipeline is built.
Thank you, Megan. So to play with all this data around us, first, we have to pre-process the information from several sources. Vocabularies, dataset, web pages, and papers from multiple domains. The pre-processing corresponding, for instance, to normalize the several types of documents we collected. In our pipeline, we address data from arXiv, Wikipedia, Science Mission Directorate vocabulary, and in UAT, Unified Astronomy Thesaurus, as Megan said. K-means is also applied to check overlapping across these multiple domains. From this data, our approach automatically extracted some terms and keywords from these domains using tools such as YAPE. We then connected the extracted words, creating a knowledge graph, which is a treasure map for us researchers. These words are connected using edges, and the linkage has been experimented with semantic similarity and co-occurrence. For the semantic similarities, we find the term bird on 2 separated datasets, one with only heliophysics and another hierarchically with both heliophysics and astrophysics texts. We then use their embeddings to compute the cosine similarity between the terms to study their relations. The knowledge graph is then human validated and also by quality metrics. And the visualization can be created with several tools, including Arena 3D, which is the one we selected for our case. Keep watching and you will see Rolene presenting you amazing visualization of our graphs.
Thank you, Marcella. Before building the knowledge graph, we wanted to verify that there's an overlap between the different domains of the NASA SMD. We use K-means for this, which is a ML-based clustering algorithm, and we checked whether the clusters overlap. On this slide, you can see the K-means clusters for abstract of planetary science and heliophysics. K-means achieved the 80% classification accuracy. We achieved this high accuracy as the algorithm can distinguish between the 2 domains pretty well, but it didn't achieve the 100% accuracy as there are many overlapping terms. Now, I'd love to show you one of the knowledge graphs that we created. Here we go. This knowledge graph was created by extracting keywords from arXiv abstracts, and the edges are based on co-occurrence. This graph looks a little bit like a bloom, and we will come back later to the term bloom. As you can see, it's like massive and super complex. This image alone just shows 1,000 edges, but the original knowledge graph has about 250,000 edges. Knowledge graphs can be very sophisticated, and we have been creating many different variations and have been looking at them from different perspectives. On this slide, you can see a multi-layer knowledge graph where each level corresponds to a level of the UAT. We are visualizing the top 5 keywords of all the archive extracts per level. We created links between the different layers if there are overlapping terms. In short, during FDL, we have considered many different variations of knowledge graph and experimented with different techniques. Now, Vexen will show you how our knowledge graph can help NASA and humanity.
Thank you, Rolene. This is what our Bloom Graph Knowledge Discovery search engine, which builds upon our knowledge graphs, could look like. Let's say that cancer researchers want to get solar radiation data. They go to the knowledge discovery and search for solar radiation. Behind the scenes, the search engine is looking at that knowledge graph to find connections to provide the best information. The search engine will then output the best data sets and potentially information that the scientists wouldn't have thought of. There is a connection between radiation and astronauts' health at the International Space Station. The scientists will not only be provided with the solar radiation data from the A satellite, but also the galactic cosmic rays data from the Voyager, as astronauts are exposed to both these radiations. And these are satellites beyond our moon. So not only does this benefit the cancer researchers, but all scientists and humankind. With this tool, we expect to at least reduce the search time by half through this high volume of information. We want to provide scientists this tool that will help them make discoveries and find solutions so that not only can we go back to the moon, but we can go to Mars and beyond. Thank you for your attention, and thank you to our partners for their incredible supports.
Wonderful, thank you. That's extraordinary. And I think it just brings to light a totally different dimension of the power of AI and machine learning tools to help us understand connections and to help us use natural language processing as a technique to sort of unravel very complex sources of information. So terrific. And we're going to jump right into the Why It Matters panel to kind of unwrap what we've just heard in these last 2 presentations. So joining us again is Massi Mascaro from Google Cloud. We also have Katie Baines from NASA. She's the Deputy Chief Science Data Officer. And from the US Department of Energy, we have Sunita Satyapal. And I believe we also have Marika Walchenko. So welcome, everybody. And love to hear your perspectives on what you've just heard. And again, since you're sort of up there in the upper left of my screen there, Massi, why don't you go ahead and weigh in?
Yes. Well, I mean, I'm super excited about these 2 challenges. Coming from Google, where our mission is to make information accessible and useful, I think this is exactly actually what we really kind of hope actually kind of will happen with technology. Let me make also an analogy and kind of a connection with the previous presentation. We always think about AI as kind of searching in this haystack of data. I think actually those 2 challenges really bring this even further. They now allow us to search into a haystack of knowledge. And this is super important for science, because science is not just kind of making inference, is understanding concept, is making connections. And these tools actually are really kind of a great step ahead in making that happen. I'll just also kind of mention that I love how the teams not only kind of applied really advanced research and NLP to find those systems, but they also kind of thought about how are we going to expose this to the end user? The end user doesn't need to be exposed to the complexity of what they're doing. And I think actually this is really essential. So I'm really blown away by both of those challenges, and congratulations a lot to the teams, and really looking forward to see how we can actually kind of make this really kind of accessible to a lot of scientists out there.
Excellent. Katie, from a science data perspective, what do you think? I think you might be muted, or
you haven't got your audio, Katie.
How about now? Good.
There we go.
Apologies. So it's really exciting to me because one of the things that we do within the Chief Science Data Office is look across all of the investments that NASA has been making in collecting scientific knowledge over the decades we've been around. But we've really historically had that fragmented into astrophysics research, earth science research, planetary research, and earth science. And it was never really intentional to tie all those things back together. So we end up with these fragmented data silos, these publications, this wealth of knowledge, and not a lot of effort been put forth to connect the dots among those. So, as we use AI/ML tools to sort of extract relevant sources of data and relevant connections, identify features, cluster the data in different ways than it's been clustered before, we're really able to amplify the useful findings and create new pathways to discovery. And I really like the example of how we can leverage radiation data, in a lot of different situations. And so finally, when I think about what this might unlock for us, and I really liked the H2 team looking at how they can match investments in the future. That's actually one of the things that if we uncover this sort of thing from NASA's data perspective, and we notice that data we're collecting for Earth science mission can be reapplied as we look to exoplanets, then we can look at how we adjust our investments in those technologies and those missions to see how we can continue to double dip or even really leverage the discovery in more than one realm. So really cool work and a really nice way to think about these things.
Yeah, that's amazing. And whether it's a data silo or a science domain silo, finding these tools and using these tools to break down the walls of those silos or look at the intersection where maybe there's more powerful insight, I think is so important. Sunita, what are your thoughts?
Great, thank you, Bill. And first of all, huge congratulations to the team. And it's been great working with you. And for us, it's really exciting. So really impressed by the creativity and just the capabilities of the team. So as you know, the Hydrogen Energy Earthshot was launched when the president asked our Secretary of Energy, how do we really accelerate progress towards the climate crisis? And I don't know where everyone's located with all the heat waves and the fires and so forth. I think we're all, really recognizing the urgency. So hydrogen is one key component. So similar to the moonshot, it's great to see, Katie, from over half a century ago, the idea of these energy earthshots are really to galvanize the global community. And hydrogen, again, is one of them, but there's huge potential to decarbonize with hydrogen. So as the team, and as Joe mentioned, we have to get to low cost. So that 1-1-1 goal, how do we get to $1 compared to, over $5, which is where we are today with electrolysis? So this approach of really rapidly being able to identify the promising pathways, how do we unlock opportunities, all of that I think is really, really critical. We have $9.5 billion now through the bipartisan infrastructure law. So again, this has been extremely valuable and look forward to following up.
Great, thank you, Sunita. Well, Marika, I'm sorry, but we're running out of time according to the music, but if you have a quick insight you'd like to share, please go ahead.
Sure. I just want to say that I think what this team has done is great, and I'm really excited to see how we can take this and expand it within the hydrogen space to things like storage and delivery, and how maybe even people working in other areas could take the same approach and develop these kinds of tools in their own areas.
Wonderful. All right, James, we're going to go from to astrobiology. Take it away.
Yeah, and I just wanted to say hi to Kaylin too. We heard from you in the film, but just again, thanks so much for supporting this team. And yeah, because of the music, we're having to obey and move forward with our next twin challenge, which is the Urban Red Hunter and the Astrobiology Biotic challenge, which of course was a bit of a challenge to find a name that suited both, but we came up with Signal and the Noise. And so with that, I'd like to introduce our Astrobiology challenge and a short film from Mary Vortek from NASA.
I'd like to welcome you today to an FDL challenge that addresses what I think is the most exciting question facing humankind. Are we alone? One of the biggest challenges that we face looking for life beyond Earth is that life and its imprint on its environment can be indistinguishable from features formed by non-biological processes. This year's Astrobiology FDL team have worked to develop tools, databases, and taken an important step forward in understanding how organic molecules that are formed biologically can be distinguished from those that are formed abiotically. I want to thank the FDL staff and the challenge team for giving of their time and creativity to this important quest.
Good morning. My colleagues and I are excited to share what we've been working on these past weeks at FDL with you. Hi, I'm JJ, and soon you'll hear from my amazing teammates, John, Timmy, and Aaron. But first, let's introduce you to our muse and fellow explorer. Imagine you're a dragonfly. Well, a special kind of dragonfly that's being built to hop from place to place across the surface of Titan, the largest moon of Saturn. It's the only other place in our solar system where we've observed liquids flowing across its surface. However, Titan's clouds and rivers are made mostly of liquid hydrocarbons like methane and ethane. More fascinating still, beneath the thick crust of ice is an ocean made predominantly of water. One of the main goals of Dragonfly is to search for potential signs of life. Among the instruments that it will use for this task is a mass spectrometer, which is capable of determining the molecules that are present in a given sample from the environment. However, on an icy world like Titan, where the average temperature is well below freezing, organisms would likely carry out metabolism and reproduction differently to what is seen on Earth. So this means that it might actually be pretty tricky to decide if what we observe is actually a sign of life or not. Our work advances the concept of an agnostic biosignature, a way to recognize life as we do not yet know it. By looking for specific features of the molecules it finds, one can tell us how complex the molecules in the mixture are. We can begin to form special fingerprints or molecular biosignatures, which can offer a more conclusive determination if it encounters strong signs of life. So what do we mean by complexity in this case? Well, we can look at the number and diversity of atoms that make up the molecule, the number and kinds of bonds that hold the molecule together. We can even consider the number of steps required to create the molecule. What we have set out to develop is a kind of threshold. Molecules below the threshold can be created by abiotic processes, while molecules above the threshold are too complex to be created randomly in larger quantities. The presence of these more complex molecules, we believe, could make the discovery of life elsewhere in our solar system more conclusive.
Just 8 weeks ago, our team accepted the FDL challenge to better define the concept of agnostic biosignature. We sat down together and set 3 goals for ourselves. The minimum goal was to curate a data set of molecules that are useful for the search of life for NASA and for the broader scientific community. The next target was to demonstrate how to use the data set and train machine learning models to speed up the computations and to infer deeper relationships between molecules and their reactions. The bold goal was to take this step further to estimate complexity directly from instrument data, for example, using the mass spectrometer on board Dragonfly. This is a critical step that would allow real-time autonomous decision-making during space missions. Today, on behalf of my wonderful teammates and advisors, I'm honored to report to you the progresses we've made towards achieving these goals. First, let's talk about the data set. For the past few weeks, we put our hearts and souls into creating this data set, which is the first ever designed to catalog molecular complexity and training machine learning models. We've collected molecules from many different sources, incorporated relevant features such as mass spec, while computing scores for complexity. This data set will be made available for NASA's future missions and for the broader community. Here, I hope to stress that dataset curation is really at the foundation of everything we do. Just like this iceberg, it is the invisible dataset below the water that keeps everything else afloat. With enough good data, you can then do something exciting and cool. That's what Timmy will show you next.
Thank you. As John suggested earlier, the machine learning part of our challenge consists of two similar but slightly different tasks. In both cases, we want to predict molecular complexity using a neural network. The respective inputs to the network, however, are different. In the first scenario, we predict the complexity directly from some formal representation of a molecule. For example, a string that describes the structure of the atoms and bonds. The main use case for the scenario is speed. Of course, there are classical algorithms to compute the complexity of a molecule, but these can be very computationally expensive, especially for larger molecules. Using machine learning to find surrogate models can help us to get good approximations in just a fraction of the usual time. To put a number on it, we are potentially talking about the difference between days and milliseconds of computation time. In the second scenario, we predict the complexity of a molecule from data that can be observed by the instruments on board of a spacecraft, specifically a mass spectrometer. Predicting molecular complexity from instrument data is exactly what we need if we actually want to use this in practice to search for potential signs of life. Nevertheless, to the best of our knowledge, inferring the complexity of a molecule directly from its mass spectrum is something that has never been done before. That is, until FDL 2022, when our team took on this challenge and started to train machine learning models exactly for this task.
Okay, and now's the point where you should be wondering, does this really work? Well, we have some good news for you today. Let's take a look at the results and you can see for yourself. On the left side, you see two histograms. The black one is the actual or calculated complexity scores, and orange are the ones our model predicted. They agree pretty well, don't they? Now look at the plot on the right. You still see agreement between the true values in green and the predicted values in orange, but there's this interesting range beyond about 10 to 20 where there is some discrepancy. Now that's an interesting place to look, because if you compare that to the histogram overlaid there, we can see this happens due to a lack of training data in that range. Now this range is especially interesting because it's very hard to calculate these values traditionally. This is where ML comes in. Also, these are molecules that are primarily important for life, as we know it anyways. The range of molecules here is a prime target for our continued research, because this isn't just a one-shot deal. Our model may not yet be flight ready. We're not flashing the firmware on Dragonfly just yet, but it's a strong proof of concept. It achieves a major first. We can go from mass spec measurements to molecular complexity and do so at blazing speed. We see an upwards of 400,000 times faster versus the standard calculation method. This is exactly what a probe like Dragonfly has to do. And the tools we developed to make this happen will be provided to the broader community. Tools built around a central concept, perhaps best described by Carl Sagan. The beauty of a living thing is not the atoms that go into it, but the way those atoms come together. Thank you.
Wonderful. Thank you, team. That's extraordinary work. And, you know, I think another example of where FDL is bringing firsts to bear on the challenges we're doing. Excellent work. We're going to stick to this theme of signal in the noise. And I'm going to allow Craig Sloan from the U.S. Department of Energy, the director of the U.S. Department of Energy's Office of Proliferation Detection, introduce our next challenge in this theme, Urban Radiation Hunter. So we'll see a short video from Craig.
In support of high-profile events such as presidential inaugurations, Super Bowls, and G7 summits, the U.S. government deploys many capabilities to respond quickly in case there is a credible threat of nuclear terrorism. One of those capabilities are Nuclear Emergency Support Teams, or NEST, which are sent out to detect, locate, characterize, and if necessary, defeat any potential nuclear threat devices. As part of their response, operators will use mobile radiation detectors to locate and hopefully identify any sources of radioactivity. The challenge is that in addition to nuclear materials of concern, such as enriched uranium or plutonium, there are other possible sources of radioactivity, such as technetium-99, a radioactive material used for medical diagnosis purposes, as well as a background of radioactivity that exists in building materials and natural radiation. Additionally, if a nuclear device is located in a building, Materials in the building can shield the radioactive signature, effectively helping to hide the device. Against this challenging backdrop, researchers at the U.S. National Laboratories have created a synthetic dataset that has placed various radioactive sources in the challenging urban environment I previously described to allow for the development of machine learning techniques that could be adopted by first responders to aid in their important mission and hopefully enable the defeat of a terrorist nuclear device.
Hi, everyone. My name is Joe, and I'm part of the Urban Rad Hunter team. And our team is composed of our faculty, Robert Burchin, Tom, James, Gregory, and also the researchers, Peter, myself, Jose, and Lindsay. So when we see a symbol like this, we automatically think about a nuclear bomb or a radioactive meltdown at a plant. But the sources of urban radiation can be more diverse than that. And just to give you an example, I just want to talk about this case called the Goiânia accident in 1987 in Brazil. And essentially what happened is two scrappers were going to an abandoned building. They came across this old medical equipment, but little did they know that there was cesium-137 in there, which is a highly radioactive material. But they took it apart because they thought they might find something valuable. And upon finding the cesium, they distributed it to lots of people in the community. And at the end of the day, there were 4 acute deaths, more than 200 people with high levels of radiation found in their body, 6,000 tons of radioactive waste generated, and of course, a community that was traumatized after this event. So all across the world, there are radiological events that are happening all the time. And this is just a map showing just events happening across the globe with darker colors showing more events. And in the 6-year period of time, there are over 1,200 reported events. And we have tools to detect radiation. For example, we have scintillators, which can detect gamma rays emitted from radioactive sources. And in pristine environments like this, these are pretty effective using traditional signal processing methods. But in an urban environment where sources might be shielded by buildings, or the buildings themselves are emitting gamma rays, which can confuse a detector, it's not so easy. And also the sources themselves might be moving around in this environment as well. So essentially this boils down to detecting a faint signal in a complex and noisy environment. And we know that machine learning is very good at detecting and identifying the signal from the noise. So the question we want to answer is, can we apply machine learning to outperform traditional signal processing methods for our application? And the goal is to develop a machine learning algorithm that can be deployed on existing detectors. And we did this by using simulated data, as the video mentioned, that was provided to us by the Department of Energy, and it simulates a detector moving through an urban environment. And here on the right is showing gamma rays dispersing through the urban environment from a radioactive source. So you can imagine as the detector is going through, it's logging all the energies. And for a given time slice delta t, we can form histograms based on those energies. And if you form histograms for every delta t, we can stack all these histograms and form an image. And we know that we can do image classification very well. So that's the approach that we took in our challenge. So given these images from lots of different runs, we want to separate the background from the source runs. And that can be done using a binary classifier. And furthermore, we want to know what kind of source is in these source runs, right? And then we can use a multi-class classifier to do that. And I'll hand it over to Jose to talk a little bit more about our pipeline and our preliminary results.
Thank you, Joe. So here's our framework. It's the RedBot. Essentially, is a tool that can detect and identify the radiation, and that can be also built into devices and run into urban environment as well. To build this, it starts with the data processing, where we take the raw data and transform it into a bunch of images and put this to train our models. Then we ensemble them a bunch of modules with different features to get better predictions on that. Right. After we assemble the model, right, we can test this with simulated data or put into the real world. So basically, is the flow of a pipeline. But this we need detection in real time. So we decided to slice the full run image into slices, the small chunks that can become our trained images, right? We separate those slices into source or not source and different kind of radiation sources. But this still classify on these slices. If a detector passing through is a part of the run that classifies a source, the next one might not be classified as the same one. And we need some other kind of approach of that. We need to see if the next, let's say, 6 runs is also source, and then we apply some heuristics to infer if there is another source and make the decision. Right? So we train our model and we get a validation around 87%. So, but this was training our model with around 100,000 images, and we are scaling up our model up to 5 million images and much more features to train it. But in fact, this after training is real fast to infer whether there's a source or not. It's less than a second to inference if there is not. And in summary, our approach is like faster than before because we don't need a full run to predict if there is not a source of radiation. We can detect in the full run during the run. We also have much more data and augmented data and applied different channels to those images with different features that can be also understood as kind of things to identify the source. And we assemble more than one model as well to get better results on that. So I will leave you with that video. With that, we can imagine a drone with detectors and the building a framework that are measuring the radiation in the urban environment and can automatically detect if there is another source of undesired radiation, that make alert and make this to decision makers to have a decision. So thank you very much for your attention. It's the red bot.
Excellent. Thank you so much. Both teams, Redbot and Astrobiology, really sensational stuff and beautifully presented as well. I wanted to introduce our Y panel. I realize there's a bit of a difference in domains here, but of course the theme is signal in the noise. And we have Craig Sloan from the DOE, Ritwik Gupta from UC Berkeley, John Karch from NASA, and Mary Wojtek from NASA. So welcome. Really looking forward to hearing your thoughts. Two sensational bits of research, and yeah, just to sort of see what you thought and what surprised you, and perhaps actually, Craig, why don't you pick up the baton, and it'd be good to hear your thoughts.
Yeah, thanks very much. No, that was outstanding from both teams. Obviously, I'm a lot more focused on the Urban Rad Hunt or the Radbot one. But you guys absolutely nailed it from my perspective with regards to understanding the challenge, but then understanding the importance of the challenge and the fact that you've got to make these decisions in near real time. And so you can't have these overly complex algorithms that will take minutes to half hour to an hour to run. The people doing that search need to be able to get some sort of determination in real time. And the fact that your algorithm that you developed is providing those results in less than a second is outstanding. And that's what we're looking for. And so, you've really done really nice work here that will have some real world applications and potentially can save lives in the future. So I think you should be very, very proud of what you've done here.
Ritwik, I saw you nodding. I don't know if you want to build on that.
Yeah, first of all, fantastic work to both teams. Clearly a lot of effort put in here. The single most common thread between both of these presentations was how they're using machine learning to wrangle this task of complexity. Urban rat hunters trying to find radiation in complex urban environments. The other team that I'm blanking on the name of right now is trying to characterize complexity of molecular data. But we don't see this often in machine learning. We're doing really well at creating new images, at generating new text in simple, sometimes unconstrained environments, but actually understanding fundamentally what makes these data complex and how can we detect them in these really chaotic environments. That's a field that's really underexplored. And these teams have done a fantastic job. Urban Rat Hunter, your work could be equivalently applicable to finding radioactive sources in new planets where we don't understand what processes cause, radiation or how different atmospheric layers could make radiation go in different directions. So really good work, really excited for the future of your projects and looking forward to how all of us can help you to get to this better future.
Thanks, Rodwick. So speaking of life on other planets, Mary, do you know what you were thinking when you saw that? Mary, did you want to make some thoughts on how the teams went? Not sure she can hear us. John, do you want to jump in? Yeah.
Yeah, so first of all, I think it was great having these two teams together. I can really see the connection between them. And, starting on the astrobiology front, I think that...
I thought this was an amazing challenge, and I just want to highlight a few things that I think the team brought up in their presentation.
Sorry, go for it, Mary.
Yeah, I mean, am I unmuted? I'm sorry.
Yes, you are now.
We can hear you.
You're good to go, Mary, if you can hear us.
Okay, so I'm sorry for the delay. I'm not sure what's going on, but anyway. Yep, okay. Anyway, I wanted to just highlight a couple of things that the team brought up. One is I love the iceberg analogy, and I think it's useful in so many instances, but particularly with the AI machine learning activities, which is curating and getting data that are really robust is essential. And so that all the work that goes into the actual challenge is really essential for progress. So I also wanted just to point out that I'm really delighted that my team in astrobiology, and I think of you as mine, developed a database that's going to have a much broader use. I attended a meeting about 6 years ago when this idea came up of doing just what they're doing, but there was available and everybody was too daunted by the challenge of pulling together the data that could be used for such a challenge. So thank you guys so much. I'm really delighted and can't wait to see where what you've done has gone in the future with yourselves continuing to be involved, but also other people getting into the party as well.
Thanks, Mary.
Thanks, Mary. Yeah, and thanks for recreating the experience of being on another planet in terms of delay. John, 30 seconds, any thoughts, reactions?
Two quick ones. First of all, I'm really excited to see all the effort into thinking about how can the spacecraft decide what is helping the spacecraft with the process of figuring out what's scientifically interesting and also what data to prioritize and send back to Earth, especially in high latency environments like, a spacecraft like Mary, or like a spacecraft, at at Titan. The instruments can often do a lot more than, we're able to tell them to do. And so having the spacecraft be able to work through some of that on its own could be very beneficial. And then I'll also say on the Rad Hunter front that some of those same, analysis, same types of analysis of spectrograms happen in a space science context and in even, space gamma ray spectroscopy and that sort of thing. And so these same techniques or close to derivatives of them could be useful for us as well.
Thanks so much, John.
Thank you, John.
There's the music.
There's the music. All right on cue. So, what John has kind of alluded to here is this whole notion of decision support. So how can AI and machine learning enabled tools and techniques help with decision support? We're going to jump now to the overall heading of disaster response. And in particular, the first team is going to talk about wildfires and using multispectral techniques and AI tools to estimate fuel loads. So to set that up for us and get the team on their way, we have a short video from David Howard, who is at the U.S. Department of Energy, and he's a power engineer there. So take the video away.
Wildfires have become a growing concern in the U.S. and continue to cause controlled and uncontrolled power outages. Mitigating these impacts begins with enhanced predictive wildfire models. The Department of Energy's Office of Science and the Office of Cybersecurity, Energy Security, and Emergency Response are funding this initiative to improve the accuracy of wildfire risk prediction. This will support actions that help reduce the number, duration, and extent of wildfires. The research will leverage artificial intelligence and radar satellite imagery of vegetation and other factors to help estimate surface fuel loads to identify areas with a higher wildfire risk. This work will help prevent fires near power lines and substations and enable control room operators to take quick corrective actions and help communities maintain power. AI will help us draw insights from vast amounts of data, enabling better wildfire management.
Good morning, my name is Carol and we are the Wildfire team. Today we're presenting the results obtained during the FDL program. Next. This is our team, the researchers, the research assistants and faculty. Next, please. So recently, wildfires have shown an unprecedented increase in their extent. Many times their control is beyond national firefighting resources. It affects overall population and land and ecosystem services managers, governments, and emergency teams as well. It endangers human lives, fauna, and flora. Wildfires impact on the landscape from months to decades, depending on the severity. In fire-prone areas, it's not a matter of if the subsequent fire is going to happen, but a matter of when it's going to happen. So in this case, a post-fire scenario becomes a pre-fire scenario for the next event. And evaluating the fuel conditions and the affected area is crucial. Next, please. Here is an example of how dynamic a fire may be. It's possible to see from only one ground photography an unburned area and a burned area with different ash colors that indicate a correlation of different biomass consumptions. Black and gray ash contain organic matter that is shared but not consumed, while in white ash the biomass has been more completely consumed. I'll now pass to Amani.
Thank you, Carol. This is how the burn severity map looks like. The severity can ranges from moderate severity to high severity and low severity. We need an urgent approaches that are adaptable, faster, and accurate to assess fire severity and post-fire fuel conditions in which the input data can be easily accessible, including for locations with complicated terrestrial accesses. The primary focus of this study is to explore how machine learning can help map the severity of the fire and how would that in turn help the fire management to identify the severity of the fire. Next, please. We are using two different data sets for this work. We're using Sentinel-2 and PlanetScope. The main difference between them is in terms of their spectral, temporal, and spatial resolution. However, these data sets comes with pros and cons for using them and their readability for machine learning. The pros of Sentinel-2 is the high spectral resolution. With PlanetScope, despite the benefit of their great temporal and spatial resolutions, these data sets require lots of data wrangling. Now I'll pass it to Huichi to walk you through our developed model.
Thanks, Amani. I will introduce our workflow and models. We first select data based on 3 fire locations, and then we clean and process them and clip them into small tiles. After we prepare the data ready for the training process, we start to build our model. Our baseline model is to do simple PCA analysis and calculate indices like the commonly used burn ratio and vegetation index to analyze the image difference. This model is easy to build, but has limited learning ability. So we also applied a contrast learning method called SimClear. We built both local and global model for it. This model has shown a stronger ability to extract representations from the images. After we have a model pre-trained in this process, we use the model to help extract features from pre-fire images and post-fire images. And then we calculate the feature distance and use K-mean to do the change classification. This helps us get a burn extent map and burn severity classes. We first compare our results to existing fire products and our baseline model results. For example, the burn severity map based on DNVR on the right side. We also have some manually generated labels. We applied 2 evaluation metrics, the PRAUC curve and F1 score, to help quantify our model's performance. I will pass to Beichen for our downstream task.
All right, thanks, Huichi. For the downstream task and validation of the SimClear model, we used the 2018 Mesa fire in Idaho as the study region. The pre-fire and post-fire conditions are shown here using the PlanetScope imagery, which you can observe the significant amount of the wet ash in the center of the image on August 15th. And one of the validation labels is demonstrated on the right side, indicating the burn area. Next slide, please. We trained 2 types of models for the downstream task validation. For the local model, we trained and evaluated based on the Sentinel-2 at the Mesa fire. For the global model, it was pre-trained on the PlanetScope dataset at the 2 different fires and then was evaluated at the Mesa fire. After running the pre-trained SimClear models on the validation dataset, we mapped the cosine distance calculated from the feature representations shown in the middle. Since the performance between the local and global models cannot be directly compared, so we then developed different baselines for each of them, and both models outperformed compared to their own baseline. 2 animations on the right side here are the magnified scene in the white boundary. You may observe the improvement in the resolution at the model output based on the PlanetScope data. You may also notice a good alignment between its prediction and the wet ash. Next slide, please. Furthermore, we performed another validation process on the manually annotated labels. They are wet ash, black ash, and unburned area. And we compared them to the major, minor, and no changes. They are clustered from the SimClear feature representations. The matrix of the different experiments set up are shown in the table on the right side. The higher the value, the better the performance. The SimClear model trained on the PlanetScope has a very promising overall performance, even though it has not been fine-tuned yet. Next, please. As a summary, here are takeaway notes and further steps. To be highlighted here, our proposed SimClear model outperforms the baselines, which hence can be used in mapping fire severity, helping post-fire field management, and benefiting local line managers. That's all for our presentation. Thank you all for your listening.
Thank you so much, team. Really exciting work, and also really appreciated the explanation of the nature of fires. Another team which is also exploring disaster response is our Fortifying the Grid team. And so I'd like to introduce the video from Pam Isom, who's the director of the ATO office at the DOE.
Artificial intelligence learns, explores, and generates systems responses in the event of extreme events or unplanned situations. For this effort, we are focused on the ability to use science and address science goals of the Department of Energy to fortify the nation's power grid over the upcoming decades, factoring multiple emerging threats to the power system is one of the main things that we are focused on addressing. AI promises to play a key role supporting the DOE's Grid Modernization Lab Consortium in optimizing critical mitigation and adaptation strategies such as line undergrounding, vegetation management, as well as planning the transition to low carbon infrastructure as our climate changes and to support underserved and disadvantaged communities. We hope research like this will allow the DOE and you to better plan infrastructure investments based on intensified and modeled risk to the system. We can't think of a greater opportunity to make a difference and change the world than the things that you are doing. We would like to thank our partners, subject matter experts, faculty, and of course the amazing research team for helping to pave the way.
Hello, my name is Trier Mortlock, and we are the FDL Climate Adaptation Group aiming to fortify the grid. The current state of the US power grid is grim. Our aging grid is subject to constant stress, and infrastructure often fails due to overdue and insufficient investment. Our nation's grid is also confronting the changing climate as extreme weather events cause a growing majority of outages each year. During outage crises, lives are literally on the line, evident in the fatal grid failure in the 2021 Texas winter storm. Power grid operators face the unique challenge of digesting and processing a storm of information in real time. While grid simulators are available for research purposes as well as operator use, these tools often lack integration of environmental data, like that from extreme weather events. To address these concerns, AI can assist grid operators in their determination of what to do next during a crisis situation. This integrated model can ingest geophysical data using the behavior of extreme weather events in order to anticipate faults and thus help determine the best decisions for the operator to make. Here are the three core proposals guiding our model design and research. First, can we realistically generate power line faults from extreme weather events? Second, can we develop a machine learning agent that recommends grid operation actions? Thirdly, can we promote equity in decision-making by informing the operator of grid action impacts on vulnerable communities? I will now turn it over to Julian to introduce our workflow and discuss the data pipeline.
Thank you, Trier. We now present GridWorld, a human-in-the-loop grid control framework for grid operators. GridWorld aims to support us in our missions to minimize energy loss and improve climate resilience while promoting equitable decision-making. Our workflow has three sections: data fusion on the left, our grid agent in the center, and then the operational interface on the right. Our input datasets consist of socioeconomic information derived from the 2020 census, meteorological data that pertaining to two extreme weather types, hurricanes and wildfires, and our synthetic grid topology, a handcrafted 118 bus design modified from the IEEE to represent the Texas power grid, ERCOT. Let's first discuss the data fusion process. This first step integrates geospatial data into the grid model, outputting the time and location of a grid fault via transmission tower fragility curves. In the case of hurricanes, we use hourly 10-meter wind speeds from ERA 5 reanalysis data. 8 historical hurricanes, 3 shown here, are overlaid onto the Texas grid topology. For each event, several fault variations are created due to the probabilistic nature of the fragility curve present at each element of our topology. An additional type of extreme weather we integrate into GridWorld is the wildfire. Because wildfire dynamics occur at a much smaller scale than our grid, we choose to model tower fragility for wildfires as binary. If a fire intersects a transmission tower, fault occurs. Let's now discuss the grid agents design with Hashmith.
Thank you, Julian. Now we present our grid agent, which operates on the extreme weather outage events generated in part 1. GridWorld is built upon GridSwap AI-compatible gem, whereby the agent interacts with the environment, comprising the grid topology, hazards, and power flow chronics. The gem environment allows the RL agent to receive observations, which it then takes actions on to receive a reward based on the survival rate and available line capacity of the system as a whole. By utilizing this framework, we are able to explore all potential scenarios with little risk to critical infrastructure or equipment. Here is the example of the actions and observations from one of the scenarios. As you can see on the right, the agent is taking multiple actions like set line status, set bus status, in addition to energy charge or discharge based on the generation and load observations on the left. On the left, you can see the performance of the 2 agents. They do nothing, that perform no actions, and the expert agent who has full knowledge about the actual state of the grid. Both struggle to perform in the face of extreme weather events as displayed with the fire icon. Our reinforcement learning agent was built with the proximal policy optimization, or also known as PPO algorithm. As shown on the right, the agent can operate in the presence of fire attack with near optimal performance. I will now turn it over to Pat to introduce our operational interface.
Thank you, Hashmat. The final part of our pipeline is the operational interface. We integrate socioeconomic data, such as poverty rate from 2020 Census Bureau, to identify the lines serving the vulnerable populations. You can see that many of the vulnerable lines that are serving low-income communities are the same as the line being affected by Hurricane Carla. With this analysis, we could predict the number of people being affected by the hurricane and plan the intervention accordingly. We identified a group of critical lines in the power grid that generally need to be fortified. These lines highlighted in red are the lines that would lead to immediate game over or blackout. This discovery can be used for long-term interventions, such as putting this specific line underground, doubling the lines, and adding power storage in the area. Again, these are the 3 modules of our GridWorld framework: the data fusion, the grid agent, and the operational interface. Now, let's imagine what the future with GridWorld would look like. Let's see how stakeholders can use our platform in action during the crisis. In the future, our system would allow the grid operator to predict which power lines and auto infrastructure may be affected by the disaster. The grid operator receives the agent's recommendation through visualization, ensuring that the recommendations are explainable and actionable. The agent would also predict the outcome of the recommended actions in terms of socioeconomic impact, so the operator can be more informed about their actions. Our system can also be used by policymakers to identify the long-term development plan by identifying the most vulnerable areas to invest on in the future. In conclusion, we developed a framework of an AI agent that could assist the grid operator in making more informed decisions by processing extreme weather events as well as socioeconomic data to ensure the security of our energy future. With that, I would like to end our presentation with a wonderful picture of the team behind this project. We would like to thank the DOE and FDL team for supporting our work. And with that, welcome to GridWorld. Thank you very much.
Excellent. Thank you, team. That was extraordinary. And again, here we are demonstrating the ability of these tools and the FDL challenges and approach to understand the future, predict the future, and prepare for the future. So we're going to jump right into the why it matters panel. I don't think we have to ask the question why it matters in this particular case, James. It seems that would be pretty obvious. Let me introduce our panelists for this discussion on the disaster response. We have Ritvik Gupta from UC Berkeley. We have Joni Bradley from the Department of Energy and Rahul Ramachandran from NASA joining James and myself. So welcome, everybody. I will ask us to keep comments somewhat brief because we're running a little bit behind schedule. But let's start with you, Ritvik, since I'm seeing you front and center on my screen.
Yeah, great work to both teams. This is really cool. As many people know, disasters have multiple stages. There's preparation, there's the response and recovery. And both of these technologies will enable us to do a much better job of the response and recovery stages. During wildfires, it's always people look at the news and say, wow, this fire is big, it must be really bad. But what people don't understand is that burn severity matters much more. The hotter it burns, the more hydrophobic soil becomes, the more roots are completely destroyed, which opens you up to flash flooding, which opens you up to all sorts of adverse events downstream. And if we don't understand just how bad the burn severity was, well, we can't do much to then respond to it. And likewise, for our power grids, they're fragile. And if wildfires or other disasters destroy them, and we don't know in what way those power systems were destroyed, they were impacted, we don't know how to control the downstream impacts of those outages. And so both teams are doing fantastic jobs of helping us respond and recover to disasters. I'm really looking forward to where some of their work goes.
Excellent. Thank you, Ritvik. Johnny, what's your take on what you've just observed?
So in short, wow. I mean, that's like the first thing that comes to mind. So I want to speak about two areas. I want to start with the wildfires really quickly. My daughter is actually a firefighter, and her and I have lengthy conversations about fires. We've never had this conversation about wildfires. So after all of this is done and at the end of my day, whereas I have been thoroughly educated, I plan to educate her in some areas that she has never brought up to me when it came to fuel loads. And maybe because she didn't think I would understand, I'm not sure, but now we can have the conversation because now I understand. I want to tell you that was just absolutely magnificent. I mean, I completely understood. I didn't have to be out there to fight a fire to understand the black ash, the white ash, the unburned areas, you know what I'm saying? So it's just great to be able to get that type of information. And now, even though I used to be against my daughter being a firefighter, it will bring us closer because now I have more fuel to put to the fire whenever her and I have these conversations. Did you catch that? Okay, yeah. All right.
Very good.
Yes, so now moving on, and I don't want to take up too much time. I do want to commend the group on the grid about using data from underserved communities, I'll say, because a lot of times that data is either not as prevalent, it doesn't have as much to it, but at least there was enough here in this case for you all to be able to add that into your model. And it's good that you started there, I would say, because that's what I was speaking to in the very beginning in the panel, is where you have these energy burdens and this energy injustice, right? And where some lights come on early, other lights may come on later on, but those individuals in those low income areas, they're actually losing more than just heat or air, they're losing food, right? And if they're low income, they can't buy that food, but they get that segment of money once a month. So it's very interesting that you use that data, and I commend you for that. It's a lot of people that would actually be very thankful to know that they're being considered when they think that they're not. I'm one of those people that pass the word, and I will do so. So with that, I'll end my piece there. Okay?
Thanks so much, and a very important perspective. Rahul?
Yeah, I don't think I need to add anything more to why, but I think great job by the two teams. I think the grid world, what stood out to me was the amazing use of different kinds of data set. That is, I'm sure it must have taken you many weeks of just data munging to handle the data fusion part of it. The wildfire to me was super interesting. I think there's immense value. In fact, when I was watching your presentation, I was thinking, how can I incorporate this into our own research to operations workflow? So maybe we can have a conversation later to see how we can utilize your work. So again, great job, both teams.
Wonderful. Thank you, Rahul. And James, we'll turn it over to you to keep us going.
Well, yeah, well, I think thanks so much to the team and thanks also to the panel. Up until now, we've been looking at the teams. They've been twins. We had one triplet, which is our physics-informed group. If you're watching closely, you'll have noticed that machine learning is going through a bit of a shift. AI is now starting to really incorporate physics into the pipelines, and it's really starting to create some extraordinary results. And so with that, I'd like to introduce our first physics-informed team, which is going to start with a small film from Avi Schultz, who's the CSP program manager at the Solar Technologies office.
Concentrating solar thermal power technology, known as CSP, generates electricity by using mirrors to reflect and concentrate sunlight onto a receiver, where a fluid is heated, stored, and then the thermal energy is dispatched to power a turbine. Traditional power cycles use steam as a working fluid, but advanced turbines that use supercritical carbon dioxide have the potential to be lower cost, higher efficiency, and utilize dry cooling, which helps to conserve water. But before these cycles can be incorporated into today's CSP plants, we need to understand the parameters and constraints in order to minimize costs and maximize power output. How can we use machine learning and optimization techniques to reduce the cost of incorporating dry cooling into a CSP plant?
Yeah, so hello everybody, and welcome to the CSP Cool Optimization team. I just want to congratulate all the teams before us and also after us to start off. It's been a wonderful showcase, and I just want to hope we can continue on with this. But to start off with, I'm going to introduce our team here. First, myself, Sean Hatcher, and then followed by Andrea, Bernd, and Will, and then along with our wonderful faculty along the bottom. And we're going to go ahead and start. And we're going to start off with the energy demand problem that we have. Currently, the main renewables we have, such as wind and solar panels, don't have the capacity to meet the demand that other dispatchable resources have. And so we use these fossil fuels and other energy sources to meet this demand at the same time. And so this is not a very sustainable way to go forth into the future. So what we're going to try to do is implement CSP. Now, what is CSP exactly? Well, first off, CSP uses in a whole field an array of mirrors to focus sunlight onto a receiver, which is going to heat a fluid, which is going to in these thermal storage tanks, which then goes to generators, turbines, and so on to the grid. Well, the main component that CSP is that we're trying to implement here is that it's a dispatchable energy source. It's able to have the storage tanks up to 10 hours of just for day, night, and for peak demand. So we're hoping that we can implement this CSP into the non-dispatchable sources, like I said earlier, with the panels and the wind turbines, to meet this new demand that we have in the energy crisis. And so, first off, why do we not use CSP yet? Well, first off, it's very, very expensive. Here in the last decade, it has dropped drastically, however, and we're trying to reduce that cost continuously. But right now, steam turbines use a lot of water, which is quite expensive, and the turbines in these plants are massive. And so, where CSP is most readily available is going to be in the desert, very dry, arid regions. And this place is going to be very costly for water and other implementations for steam. And so what we're going to try to do? Well, we're going to try to implement air cooling instead, along with a new technology such as supercritical CO2. We're withdrawing all the water out of the system and using the new air cooling and supercritical CO2 turbines to actually produce this new, more cost-efficient energy production. And so with that all being said, I'm going to pass it off to Andrea to discuss Team Solair's optimization results to reduce the cost in these dry cooler.
All right, yeah. So thanks, Sean. So
But what does solar do? So, well, the technology is so new that we really started building something from the ground up. And we gather some data about weather in different cities in the US, physical correlation describing the heat exchange in the dry cooler, and cost data from Department of Energy and expert knowledge. And then these are the inputs to our simulator that we built that simulates the inner working of the heat exchanger, and then which is then used to optimize the design and ultimately come up with an optimal design. So how does the simulator actually works? Well, first we discretize the problem both in the direction of air and in the direction of CO2, as you can see here on the left. And then depending on the design, so the diameter of the tube, the fins, and the fan power, we solve the thermodynamical equations iteratively. And this allows us to calculate with great accuracy the heat transfer coefficient throughout the heat exchanger and maintain the CO2 in supercritical state, which is very important for maintaining the plant working. And so with this, we can test any possible design, but of course, this is clearly not feasible because the parameter space is extremely vast. So what do? We need a clever way to iterate over these designs. And the way we do it is using a truss region Bayesian optimization technique, which is a very fancy way to call a method that cleverly selects where to explore the parameter space based on the level of trust that it has, that a minimum is in fact in that region. And this dramatically improves sample efficiency and with respect to other optimization techniques. And what this all machinery allows us to do is this. So the model starts with a random design that is far from optimal, and then it progressively improves the design, maintaining the CO2 supercritical, and also satisfying the thermal constraint that are imposed by the power cycle, and eventually converts to an optimal solution in terms of cost. And now I'll pass it on to Will to tell you about how much better this solution is actually with respect to our baseline.
All right, let's take a quick look at our reference design, which is the current state of the art in terms of air cooling of supercritical CO2. And we estimate the price to be around $670,000 throughout the entire lifetime of the cooler. Now, using solar and our Bayesian optimization pipeline, we managed to bring down the cost all the way down to $197,000, which is about a 70% discount. Note here that the fans in these visualizations are the same size, so our cooler is actually much smaller than the reference. So not only is it cheaper, it's also much more efficient and compact. Right? So what's different between our optimal design and the reference design exactly? Everything is about 50% smaller, including the fin pitch, which deceptively enough means that there's a larger number of fins per unit length, and this is where we're getting most of our cooling efficiency from. Right? And here's a quick sensitivity analysis for how each parameter affects the cost. The way to think about this is that assuming all the other parameters are fixed, moving one parameter to its optimal value can give a reasonable discount. It's also possible it would actually increase the price. This highlights the fact that the cost landscape is highly nonlinear, and one really has to optimize over all these parameters jointly to get this combined 70% discount. And now I'll pass it over to Bernd to tell you about the future of solar.
Thank you, Will. So we've now seen that our solar simulator gives us an optimized air cooler design for any location on Earth. To put this into perspective, I'd like to show you two global maps of the annual solar irradiance on the left and the availability of water on the right. You can clearly see that there's a lot of overlap between regions with large amounts of large amounts of solar energy and regions with small amounts of water. So what an optimization of an air cooler design allows us to do is it allows us to expand CSP to these arid regions where there's not enough water. We can also lower the cost of those plants, and it gives more people on the planet access to dispatchable renewable energy. So now I'd like to take a step back. As a species, we already have developed all of these beautiful renewable energy technology. We're now looking at a future where AI and ML methods will help us make use of these technologies in a better and more effective way. To make this happen, we are working closely with industry partners, shown on the top right, that are ready to take this to the field. Of course, there's still a lot of work left to do for us. We want to add more features to make our simulations more realistic, and we want to generalize our approach to include more possible designs. With that, I'd like to thank my teammates for their incredible work, our partners for their ongoing support, and all of you for your attention. Thank you very much.
Wonderful. Thank you, team. That's outstanding. We're going to jump right ahead and stay on our theme of physics-informed modeling and discuss the topic of environmental remediation. So to set us up and to introduce the next topic, Dr. Haruko Wainwright, affiliate scientist at the Lawrence Berkeley National Lab, will educate us through this short video.
Soil and groundwater contamination is a worldwide problem. In the past 30 years, DOE has been leading the technology development to clean up such contamination and also the simulation capabilities to assess the future risks of these sites. Recently, there are concerns about the impact of changing climate, a shift in the water cycle, and extreme rain events potentially remobilizing residual contaminants. It is a challenging task for site managers to take actions since there are significant uncertainties in both climate projections and in groundwater systems. The ability to assess the future groundwater contamination under climate change will be really powerful for protecting our water resources. We thank our partners, faculty, and researchers for pioneering this work.
Hello, everyone. We are the Digital Twin Environmental Remediation team. Today, we're going to share our effort on the most important human need, water. So water safety is critical to human health. 50% of our drinking water comes from a hidden world beneath the Earth's surface, which is called groundwater. With the climate change, we often think about if we have enough water to use. We might overlook the toxic contamination in the water. Here is one contamination site near the residential area. Contaminants would be from the industrial or agricultural activities or Superfund landfill sites, and any extreme precipitation from the climate change might push the toxic contaminants towards the groundwater and drinking wells. We actually have thousands of contamination sites in the US, and 2 million people are near those sites, especially disadvantaged or minority communities. Wouldn't it be nice to ensure good quality for the future generation? However, it's a difficult task for site managers to decide whether and how they should take actions to protect our groundwater. If they have a tool like these multiple slide bars, then they can visualize the spatial temporal variations of the contaminants level, what we also call the plume, for the next 10 years, 30 years, with various climate projections that could be wet or dry with uncertain subsurface properties. Then they can make smart decisions before something happens. For example, those contaminants reach to the drinking well. Then in our digital twin project, we leverage the machine learning to help us deliver rapid plume evaluations under climate uncertainty. We have flow and transport physics simulations to provide a training set. And the biggest strength for our approach is that we can incorporate all uncertain climate scenarios from the global climate models and uncertain soil and subsurface properties from the local groundwater sites. We are integrating global climate and local groundwater models, so we call our digital twin multi-scale digital twin. This mod-to-scale digital twin would enable a fast plume prediction, predicting the spatial temporal plume variations with realistic climate projections. Now let's see our great FDL team. Ileana and Takuya worked on the climate data analysis and clustering. Aurelia and Lijing worked on the plume emulator. We also got very strong support from our beloved faculty team. Now let's go back to a more in-depth view of how we're going to tackle this problem. We perform a detailed climate analysis, classifying the entire US into a set of representative climate regions using unsupervised learning, so that we can quickly access the climate data for any target location. This analysis provides realistic historical and future inputs, including variables like precipitation, water goes in, and evapotranspiration, water goes out. We also use uncertain subsurface parameters like the permeability, which indicates how fast the water can travel through the subsurface. With this, we develop a machine learning emulator capable of producing realistic contaminant plume predictions through time. Behind the scenes, this emulator solves partial differential equations faster, which is suitable when working with complex flow and reactive transport. Now let's see our actual predictions. I'm going to hand this over to my teammates, Aurelian.
Thank you, Lijing. So to demonstrate the capability of our model, let's take a look at an example. We're going to change one input parameter, the recharge, while keeping the rest of the inputs static, and see how our plume prediction changes. Recharge is the amount of water that gets into the soil and reaches the groundwater. Typically, increasing the recharge means that there is more water present in a system and therefore remobilizes contaminants or causes dilution. Let's start with a very low recharge value. So with this value, the contaminant plume looks like this. Now let's increase the recharge by 6 times and see what the model predicts. We can notice from the difference between the two predictions that in certain regions, the concentration is higher, shown in red, while in other areas, mainly on the boundary, the concentration is lower, shown in blue. If we increase the recharge even further, this trend may look the same, but upon closer observation, the concentration increases are not as widespread and are more localized in certain areas. This just goes to show how complex these physical systems can be, but mainly highlights how technologies powered by artificial intelligence can differentiate between nuanced relationships and effectively make predictions. We tested our models on unseen data and were blown away by the results. Here is a randomly selected sample where we predict our contaminant concentration, give it some input, and compare the results to reality. Visually, the prediction is nearly identical to the ground truth. Only when we plot the differences between the two can we notice the tiny errors made by our model. As a matter of fact, the majority of the testing cases gave us accurate predictions. Further tweakings and optimization methods could be applied, but as of right now, our model gives us the correct overall trend of contaminant flow and transport. We successfully developed a machine learning-based multi-scale digital twin. We reduced the dimensionality of climate models into representative regions, while also minimizing the computational burden of contaminant transport simulations in groundwater by creating an emulator. This emulator supports rapid decision-making for site managers and can evaluate spatial temporal contaminant variations instantly. We also developed an unsupervised approach to reduce the dimensionality of the vast historical and projected climate data. The lower dimensional unique climate patterns helped us quantify reliable future recharge rate projections immediately without having to download large amounts of climate data. We think this is a great starting point. Our future goal is to make this tool available at any site globally. To accomplish this, we need a more generalized, location-agnostic physical simulations and unique climate patterns globally. We are also going to build a user interface for site managers and local agencies. With the uncertainties of climate change, the flow of toxic chemicals in groundwater needs to be closely examined to ensure safe drinking water. Thank you everyone for listening to our presentation. We really hope you enjoyed. Now I'll hand it back to the MCs.
Thank you so much, team. It's slightly overwhelming to see all this work back to back, but we have one more for you. We now have the CO2 sequestration team. We're going to have a short film from Darren Domaney, from the US Department of Energy to explain the context.
Right now, much of the world is committed to transitioning to a low-carbon global economy by 2050. Carbon capture and storage, also known as CCS, is among the various approaches being implemented to help meet aggressive decarbonization goals here and abroad. The Geomechanics for CO2 Sequestration challenge exemplifies new and innovative approaches for ensuring that the geologic storage of CO2 is done safely with no impacts to human health and the environment. The work being done here advances our ability to monitor and maintain secure storage by understanding with greater certainty how the subsurface behaves as a carbon dioxide storage reservoir. With CCS now poised to be a growth industry, this type of research is more important than ever. On behalf of DOE's Office of Fossil Energy and Carbon Management, I extend my thanks to Lawrence Livermore National Laboratory and the faculty, advisors, and researchers for their innovative thinking and contributing to this important area of research.
Welcome, everyone. We are the Geomechanics for CO2 Sequestration team. I'm Akshay Suresh, together with fellow researchers, Alex, Giuseppe, Han, and an accomplished group of faculty. We bring interdisciplinary expertise to tackle a challenging problem. Climate change is a reality affecting all of us today. Combating climate change requires us to pay off our enormous carbon debt, reaching carbon neutrality by 2050 and negative emissions thereafter. Renewable sources of energy, such as solar and wind energy, are futuristic, but cannot thaw away or chip away at our carbon debt. Biological reserves, such as forests and phytoplankton, cannot operate fast enough to avert human-made climate change, and therefore we need to act quickly ourselves. One promising avenue is geologic carbon sequestration, which we show in the bottom right figure. In this method, we trap the carbon dioxide generated in factories and power plants and store it underground as a supercritical fluid. However, one big concern here is that by injecting carbon dioxide or any other fluid underground, you increase the pressure in the subsurface, and that may lead to earthquakes. One notable example is earthquakes associated with underground fluid disposal in Oklahoma. In the figure on the right, the red curve shows the fluid disposal rate, and the black curve shows the observed seismicity in Oklahoma. Notice how the black curve shows a delayed response to trends seen in the red curve. And therefore, we have to play a very careful game. We need to store large masses of CO2 underground while minimizing the seismic hazard. And this is where seismicity forecasts enter the picture by helping us regulate the pace of injections to ensure safe commercial operations. In this regard, how do existing seismicity forecasts perform? The answer is we have a mixed response. Here is a graph showing the time series of cumulative earthquake counts seen in Canterbury, New Zealand between 2010 and 2012. The black curve is our data. The colored curves correspond to various models that have been fit to the data. As you can see, the blue, pink, and gray curves represent are highly inaccurate. In contrast, the orange, green, and red curves are more accurate. However, these more accurate models are extremely slow, needing 22 hours of preparation time. They're highly resource intensive, needing supercomputers to function. And finally, most limitingly, one needs PhD level expertise to operate these models. Let us crunch some numbers to assess the seriousness of these limitations. To reach carbon neutrality, we estimate needing about 30,000 sites globally. If at each site, say that model tuning needs to happen once every 5 days, then we need about 6,000 analysts operating these sites. This number is about 60% of the global seismology community, and that would make current methods highly non-scalable. What if we could enable scaling with speed and accessibility improvements? Giuseppe will now tell us how our efforts address these concerns.
Thanks, Akshay. This is where our tool, SAFE, comes in,
and our first most dramatic success. We've reduced the total time to construct the physics model from a whopping 22 hours to under 2 minutes, and that's just on a tablet. How do we do this? Well, there are 3 key ingredients. The first was to update the existing codebase to use best practices from numerical software, such as vectorization. The second was to reduce the complexity of the original physics model so that we could achieve the same performance with a fraction of the parameters. And finally, by using more powerful and more adaptive optimizers, our models are ready to go in just a few iterations. Now, beyond speeding up the code, these improvements also make the code quite modular, which is in turn a big win. All of the optimization and data processing is taken care of automatically and under the hood. This means you don't need a seismology PhD to run our code. Anyone with some programming experience and basic knowledge of statistics can now be empowered to generate forecasts. What's more, we're releasing both our code and our data open source, so the public is free to learn and tinker. Now, to quantify what this means for CO2 sequestration, let's revisit an earlier calculation. Remember that we're trying to remove one pain point, the need for expert earthquake forecasting personnel. Now, before we needed 60% of the world's seismologists. Let's be conservative and say that our tool needs 10 times speed up after results have been analyzed. This still means one analyst can do the work of 10. And what's more, because our tool is more accessible, we can draw from a wider pool of talent. 600 analysts from a pool of 5 million people with basic computer science skills, that's a lot more feasible. Our tool is fast and easy to use, but you're probably still wondering how accurate and how reliable are the models? The answer is that it depends on how far ahead you want to forecast. We've designed different models that are reliable across a variety of timescales. From the plot on the left, you can see that the physics model, after examining 2 years worth of data, can forecast the general trend of seismic activity for another year. You can see, however, that there are also some gaps where it either over or underestimates in the short term. Now, we can address this with machine learning models, which we can fine-tune to give us very accurate predictions over much shorter timescales. This model looks at the past 16 days of activity and forecasts the next week. Note that these forecasts also come with uncertainty estimates that allow us to determine how confident the model is about its predictions. So where do we go from here? As any ML person will tell you, the biggest limiting factor for research is the amount of data you have. And for us, the frontier is all about working with more diverse sources of data. Thank you. At present, each model is very site-specific, which is an obstacle for sites that have collected less data. Leveraging more data also allows us to use more cutting-edge machine learning models to generate even more accurate forecasts. We're excited by 2 opportunities. The first is transfer learning, wherein one model is trained on data from multiple sites. Here we can combine the best of physics and machine learning to construct hypernetworks that predict the parameters for physics-based models. So the second promising direction is just to use more diverse data sets. At present, we're limited to sites that have collected injection data, but there's a wider catalog of unlabeled seismic data and also simulation data, which can be used for unsupervised representation learning. So let's recap. For CO2 sequestration to successfully combat climate change, it needs to scale up its capability to generate earthquake forecasts. Before FDL, the skill level required for this was a seismology PhD, and the total model preparation time was 22 hours. Now, just by importing SAFE, someone with basic programming experience can prepare a model in just 2 minutes on a tablet. We're eager to see what this increased speed and accessibility can do in the fight against climate change. Thank you very much.
Thank you, team. That was wonderful. And that was an extraordinary, wonderful ending to all of the team presentations for this year's FDL program. But we want to, once again, have some additional perspectives to help us unwrap these 3 presentations on physics-informed modeling. So let me introduce the panel who will help us unravel what we've just heard about from these 3 great presentations. Joining me and James is once again Masi Mascaro from Google Cloud. We also have Alexander Lavin from Pasteur Labs, Darren Damiani from the US Department of Energy joining us as well. So welcome everybody. And maybe Alex, why don't we start with you, since I'm seeing you up there in the corner of my screen. And what did you think?
Yeah, thanks, Phil. Well, of course, I want to say thank you to the teams for the efforts and everything. It looks very elegant and smooth in the presentations, but behind the scenes, there's so much sleepless nights and hard work that they all put in. my perspective on this is exciting in a way where we are right where machine learning research meets industry, and industry that is very unfamiliar to these methods, to any data-driven type of intelligence, let alone trusting those things to take them to the field. So having the conversations with mechanical design engineers and forward deployment engineers in the field, and talking to them, and just even trying to tell them what is data, how to build a machine learning model, let alone show them results and communicate results and build a system like the concentrated solar power system, where I recall one of the engineers saying, I don't want to deliver one design, I want a million. And just like, oh, we can generate synthetic data and give you a posterior of results and run optimization objectives over this. And those are words that that engineer has no idea what they mean or how to put them together, but we can build the thing and they can derive value. So that's the part that really excites me. And I think FDL is a unique opportunity to kind of cross that gap.
Yeah, that's a great perspective. And I think, crossing that gap is so important. And again, what's interesting to me about these presentations and these last challenges in particular is developing tools and techniques where the expertise that goes into the development is extraordinary, but one of the benefits is the expertise needed to deploy them is much less, which means they're more likely to be deployed, be useful and impactful. Darren, what were you surprised by anything did you see that you saw? And what, from your perspective, are your thoughts regarding whether you were whether your expectations were met, exceeded, or underwhelmed?
Oh yeah, I mean, there's a common theme, which is great to see, and that is that AI being used as a forecasting tool so that we can be more proactive in decision making as opposed to reactive, especially when it comes to hazards. In the presentation we heard earlier about the contamination tracking and for geologic storage for us in avoiding induced seismicity. But yeah, I think for the amount of time that the researchers put into this in 8 weeks, I mean, it's astonishing. They hit all the things that we're certainly looking for, right? This idea of taking complex information and processing that in a very rapid amount of time, so from 22 hours to a matter of minutes, but also addressing data sparsity. This is another common theme within the subsurface, where you only have a limited amount of information. So how can you process that and get meaningful results? So yeah, quite astonished at the work they did, and very excited to see where all that goes later as we incorporate that kind of finding into our program.
Yeah, absolutely. And that's what's exciting, the actual deployment of what the team's achieved. And really, as you say, it's so much about decision support and seeing the future and reacting to that instead of seeing what's happening or what happened in the past and reacting to that. So time travel is really emerging. Massey, what are your thoughts?
Well, I'm blown away. I'm not surprised. But I mean, I want to actually also kind of point out something that I think is very important. I mean, the three problems that those teams resolved, I can't think of like three problems that actually are more important in today's world, right? I mean, if you think about energy storage, water, and CO2 sequestration, they're kind of really at the core, and applying AI to those is really important. I'm a physicist, so I love this idea of applying AI and physics together. I think it's really transformational because in many problems, we just can't use AI by itself. We either don't have the data or data gathering is clearly too expensive. I mean, think about this solar concentrator, the cooler optimization, problem. Like, I mean, we couldn't just build actually a lot of coolers just to gather the data about them. So the idea of using simulation and using what we know about the physics process is really transformational applying to AI. But also I love actually how some of the teams actually took this even beyond and now applied AI to speed up physics simulation, right? Yeah. And that actually is another kind of super transformative thing. So like, really congratulations to the teams. I mean, this is really kind of cutting edge, and it's really kind of applied to some of the most important problems in our world.
Yeah, absolutely. And I think you touched upon something interesting here, because it's not just about physics-informed AI, it's also about AI-informed physics, right?
Absolutely.
So, yeah, absolutely. James, some closing thoughts on your side before the the fun of the awards ceremony?
Well, again, just to echo everyone's comments, really, we started FDL to tackle these sorts of problems, and just really, it's phenomenal to see, real genuine traction, and hearing the comments from you all, so inspiring as well. And again, thanks to the teams. We're just about to change gears and go into the Innovation Awards, or sometimes we call them Collaboration Awards. It's a little bit hashtag awkward, because when we started FDL, we only had a few teams, and so there was easy enough awards to go around, and it was sort of fun. It's like everybody gets an award. But now we've got 13 teams, and we've still only got the same awards from when we started. And so there's a sort of, but the whole point is that everyone's done amazingly well. And this isn't about, it's not a competition. We use this word co-opetition. The reason FDL gets the results that it does is because we create a culture where everybody helps each other. And that's really the special sauce. That's the thing which, makes the difference. That's the thing that allows us to do what we do. So this is a thank you to everybody, researchers, faculty, but also the enormous community who've helped these teams get to where they have. And I think you'll agree, this is, quite amazing. I don't think, certainly, I always get a bit emotional at these points, because when you see so much amazing work back to back, it's quite hard to sort of take in.
No, it's
but
I don't want to contradict someone that I consider to be far more insightful than myself, namely you. But when we started FDL, I don't think we sort of dreamed about the kinds of sort of impactful results that have been presented today. But really, at that very beginning, as we talked about at the beginning of the program, it was like, can AI and ML tools be applied to basic research and to fundamental questions of importance to agencies like NASA and the Department of Energy? And I think we answered that question. Can interdisciplinary teams work together on curated challenges in a very intense short time frame sprint and get something meaningful accomplished? I think we've answered that one. And what was accomplished today now has taken us over to that arc through demonstrating the power and the impact and the utility of what these teams have accomplished. So just extraordinary work.
Should we do some awards? All
Yeah.
right. So I think let's play the film, and we'll come back with Bella and Eva, who are going to take us through the awards.
Hello, my name is Thela, and this is my partner, Eva. At this time, we'd like to present the FDL 2022 Innovation Awards. The selection process was not an easy one, and we do acknowledge the incredibly dedicated research and contributions made by all of our teams and participants. Our first award is for the most dramatic pivot. Pivoting is an action taken when unexpectedly new opportunities arise. Sometimes this means starting completely from scratch after so much commitment has been put into one idea. The Most Dramatic Pivot Award represents these changes in direction, at times when the change is unwanted, but certainly necessary. Eva?
Thanks so much, Bella. This award goes to Andy Smith and the Seismic Insights within Geomagnetic and Ionospheric data team. And I just want to call out the researchers by name, Asadullah, Debrat, and Luke. We'll tell you about some of the feedback that faculty provided in selecting these awards. And just so that you can hear why you're chosen for this. So in a challenge where failure is the most likely outcome, it can take forever to find focus. The team spent half of the 8 weeks building up model architecture that they thought would provide a safe deliverable, but it turned out to be less and less promising. We want to highlight Andy, and there was feedback about him because he dove into the details of the data from a few major earthquakes and not only inspired the team, but also changed the team direction. So indeed, amazing and inspiring research by this team. They may have solved a shared world goal of the prediction of earthquakes. So I can't think of a more dramatic pivot than that. Congratulations to all of you.
Our next award goes to the most useful contribution, and it speaks to what defines that contribution. In machine learning, it's often hard to spot the thankless task of data preparation on behalf of the community or the application of a freshly minted ML methodology to a new domain. In some instances, it's something that widens our perception of what's possible. The most useful contribution can be any and all of these things, as long as the beneficiary is all humankind. Eva?
The winner of the most useful contribution award is the Geomechanics for CO2 Sequestration team. So I just want to call out the team members, Akshay, Alex, Giuseppe, Han, and the faculty, Constantine, Alex, Kayla, Christopher, and Corbin. And just to provide the feedback that was shared about you, the CO2 sequestration team have done an outstanding job of putting their interests of building the fanciest ML model. And second, they've put their interests second and eliminated a real pain point of the CO2 sequestration industry. 6,000 seismology PhD analysts are required to forecast earthquakes with current methods at all CO2 sequestration sites necessary for climate neutrality by 2050. The team has reduced their training time from 22 hours to 2 minutes on a tablet, as you all know, reducing the number of analysts from 6,000 to 600, and simplified the tool so that only basic data science skills are needed for the forecasts. The work is celebrated by seismology experts, and there are plans to incorporate this work into the public Orion forecasting toolbox. Useful is an understatement. Congratulations.
Our next award is Unexpected Discovery. Just like dirty dishes helped the discovery of penicillin, and melting chocolate bars triggered the creation of the microwave, the Unexpected Discovery Award represents the ability to stumble upon a breakthrough. As Plato once said, science is nothing but perception. Eva?
The winner of this award is the Digital Twin Environmental Remediation team. And I just want to call out everybody again. We have Aurelian, Ileana, Liqing, Takuya, and the great faculty members, Haruka, Satya, Zakshwan, and Alexander. So the work done by this team actually led to improved and more realistic simulation parameters. So it was unexpected because the data actually found the team found a correction in the simulation configurations responsible for generating the data. So the team's extensive insights led to generating more realistic simulation data, which in turn led to an overall better FDL work product, as evidenced by the results. Congratulations, team.
The next award is the Heroic Comeback. The Heroic Comeback Award acknowledges that when discovering something genuinely new, first you might have to fail. Yet that's only a part of the story. Simply failing isn't enough. Getting back up, learning, evolving, and trying again is how legends are made. Eva?
This award goes to Fortifying the Grid, and we want to highlight Julian Arnheim and Pat Pataramutaporn. Julian was able to make significant contributions to the overall work, even with his limited coding experience. He continuously jumped on tasks, including coding, and was able to bring the team to the finish line. The grid actually initially fully committed to focusing on hurricane attacks until the realization that these were too harsh on the simplified grid being used. They had to shift to wildfires, and Pat quickly enabled the turnaround to provide the results needed to train their RL agent. Congratulations.
Next, we move to collaborative spirit. The Collaborative Spirit Award is the representation of FDL's beating heart, interdisciplinary research. It supports the idea that to achieve great things, 2 and sometimes 20 minds are better than 1, and that the exchange of knowledge is the key to successful outcomes. Eva?
Yes, and sorry about that. I meant to shout out to Trier and Hashmath and Nadia and Tara and Ahmed on the previous team. I just want to make that clear. So this is a team effort, though we just wanted to highlight those 2 guys because of the feedback received. All right, back to this one, collaborative spirit. Collaborative spirit goes to the Applied Physics Laboratory 4Pi EUV Irradiance team. The sun is a fully resolved star. The Helio 4Pi team have done an incredible job working together and helping each other learn and grow across many time zones. They also helped others working with the NVIDIA DGX servers. The 4Pi team were fully committed during the program to working together and to staying together through thick and thin. They pair coded throughout the entire program and put the goals of the team ahead of personal goals and built a nourishing and fun culture where everyone felt cherished and welcome. So just let's shout out to Benoit, Margarita, Mira, Robert, and faculty, Andres, Angelos, Anna, James, and Sairam. Amazing, thank you.
And then we have our Night Lab Award. The Night Lab recognizes the team member that went up and beyond, working both day and night in time zones spread across the world to make that FDL magic happen. FDL big. Eva?
Thanks, Bella. This one was a tie, and it was related in both cases to Australia. So one winner is Lillian from SMD. She is based in Australia, and she was routinely working through the night to stay in touch with her team. She took part in formal reviews in the middle of the night and presented her team's results without a hitch. So thank you for putting in that work. And then on the other side, we have Beichan, who was working with team members in Europe and Australia, also routinely working late and on weekends to get pipelines built and refined, jumping on calls in the middle of the night. And he went above and beyond, finishing crucial experiments late in the night to get his team unstuck. So yeah, Australia got us, but you guys were able to meet it. So thank you so much for all that hard work and sleepless nights. Oh, Bella, I think you're muted.
I am. Our final award is called the Steely-Eyed Operator. In every FDL project, there is a moment where everything can go wrong, and it does. This is the implicit contract of a high-risk, high-reward research. If you don't go through this, then your work isn't challenging enough. Remaining clear-eyed and level-headed in this moment is a rare quality, and without it, FDL wouldn't deliver. The Steely-Eyed Operator Award acknowledges the efforts of a faculty member who has regularly been the calm voice in the eye of the storm. Eva?
Okay. So steely-eyed may not be the first thing that comes to mind when you think of Andres. The first thing you might think of is how ready Andres is to offer a kind word or a piece of wise advice. But if we think of the steely-eyed operator as that calm voice in the storm, then Andres has certainly been the calm in the storm that is FDL. He has been with FDL for 7 years, and his experience shows. And it says everything about him that he has made every effort to share this experience and support, not only with his own team, but with all the challenges. FDL would not be the same without Andres. Congratulations.
And thank you so much, James.
Yeah, thank you. And I just wanted to jump in actually with Andres. Andres has been with us for 6 years, and every single project has been a real home run. It's phenomenal. I mean, as Eva said, high risk, high reward. You know, we don't expect that level of consistency, but the way Andres has really helped us evolve the process of FDL, and he's really been a massive thought leader in terms of really how to get the best out of collaborative ecosystems like the sorts we build. He's been a true colleague, an amazing thought leader, and we're very grateful for his contributions. So thanks, Andres. And I think that's kind of it. We're, again, unbelievably, you know, what a journey. And, you know, it's phenomenal to have all this work presented, you know, so lovingly by you all. And really, you know, at this point, all we can do is just sort of say thank you so much. We're in awe of what you've done. We're phenomenally proud. Wanted to say thanks so much again to all the people behind the scenes. I know, Bill, have you got any words of wisdom?
Well, I mean, I can't offer more wisdom than the teams presented today, but I think it was an extraordinary day. What the work you've accomplished in these 8 weeks has just been, you know, off the charts. But more importantly, your ability to articulate these complex challenges, the approach you took to make progress against them, and your ability to present the results, explain your methodology, you know, succinctly and concisely and impactfully was just marvelous. That's not an easy thing to do. It seems to me that every team exceeded expectations in, you know, trying to bring all of this extraordinary and complex work down to these, you know, short 10-minute presentations. Just amazing. And again, I can't thank our faculty and our corporate partners enough for all that they do to make the FDL program possible. And, you know, Google Cloud in particular, providing the extraordinary compute resources that they have been providing now for many years. FDL just couldn't happen without it. And I think, James, we've talked about how just in the first 5 or 6 years of the program, the compute went up by a factor of 700 or some extraordinary level.
I think we should recalculate that. I think
we need to update that calculation. And NVIDIA as well helped with the compute, with the, you know, they're providing the GPU compute resources. So unbelievable. And our faculty extraordinary, and you know, and our partners at NASA and DOE have been so wonderful throughout this process. So congratulations again to everyone for an extraordinary effort. Of course, we have, you know, the deep dive science presentations that will be coming up in September. So we'll be looking forward to those. And I guess, yes, it's a good time to thank all the folks behind the scenes. Rebecca, who's our Director of Communications here at the SETI Institute, Lee, who does our communications and website management and graphic design. Debbie Collier's our Director of Grants Administration, which, you know, is indispensable in actually bringing all the resources together to bear on this problem, with support from Yvonne Nicholas in contracts at the Institute, and Armine for all her tireless efforts in the endeavor to bring these extraordinary researchers from all over the world, our Director of Human Resources, and of course, Bella, who's been an FDL program manager together with Eva this year. So thank you to all of you.
And then, of course, FDL is a partnership between SETI and Trillium, and I just wanted to really call out to the, you know, huge efforts for the Trillium team. Really, I mean, you guys know what a kind of huge Herculean effort this year was. Yeah, I mean, I'm not sure if the climbing Everest is the best analogy. We'll work on the analogy, but you know, that's the gist. Is it's a huge team effort, and lots of work behind the scenes, and also just to shout out to Richard, and who's our data manager. You know, a huge amount of you know, wrangling to get all the compute resources working, and Belina, of course, our storytelling expert, who really helped the teams craft such beautiful explanations of their research. So I think just in closing, also, we have a fantastic machine learning advisory group, Yaron Gal from Oxford, Chedi Rassi from Ubisoft, and Sida from NVIDIA. These folks have been working with every team, really trying to pull the best and find the best ways through these problems. And of course, our wonderful colleague, Jonathan Knowles, who set the scene and reminds, of course, us about the importance of mindset and working together and just the magic stuff of collaboration. So with that, thank you, everybody. Really, this is where I get emotional. Better keep me away from the gin and tonic.
Yeah, right. Maybe
really,
for a little while.
Yeah, really fantastic. And again, thanks so much to NASA, the DOE, Google Cloud, USGS, Intel, Luxembourg, NVIDIA, Pasteur, and Planet. Really wonderful community this year, and we'll see you again soon.
Yeah, and thanks to Earth Coast for a great job producing today's event.
Thanks, Earth Coast, too. Yeah.
All the best, everybody. Congratulations.